paper one, because the paper one is a very important part of your assessment, and it is set up in such a way that you can really do what you can do to maximize that portion of the assessment. So after you have completed your SBAs, your next paper to say, okay, after I would have scored as much marks as possible on my paper one, on my SBA, we now start to think of the paper one as that paper to say, okay, we want to see how we can also maximize the marks on the paper one. And then now the paper two now, based on your preparation, will essentially determine how well you're able to do on the paper two. But as I said, we have a few more minutes before we officially begin. So if you're able to access that multiple choice paper again, just ensure that you attempt those questions before we begin. We have some questions on screen here that we're going to be going through. So as we go through, you're going to get an opportunity to see how the questions are broken down in terms of what the question is really asking for, how to arrive at your correct answers, and we'll also go into deep discussion because, again, as I said, leaving this session, I want us to really have a solid appreciation for electricity and magnetism, not just able to answer the questions. Yes, you want to do that as you're preparing for your exam, but also to be able to really understand what the question is really asking and how to apply the principles. So just a few more minutes before we begin. All right, again, there is some multiple choice questions. The link is in the messages. You should be able to access it. If not, you can just indicate and I will resend the link so you can engage those questions. All right, so we're going to begin. All right, so we're going to begin. But before we begin, I just wanted to have on display here the section D of the syllabus, right? Which essentially gives us a complete overview in terms of what to expect, or what are the possible related assessment questions that will be related to section D of the syllabus. Because if you were to go through the syllabus, especially in this case now for section D, you will see that there are certain specific objectives, right? And these specific objectives are essentially what you as the examiner is expected to be able to know, or to be able to actually display in terms of your knowledge and your use of knowledge. So we see we have some specific objects. So it says, okay, for instance, it says here under electrostatics we need to be able to explain the charging of objects, and we should be able to explain the terms explain in terms of the properties of electrons and so forth. So this syllabus right here gives you a complete overview, and as we're going through the questions, we're going to come back to the syllabus just to see, okay, how the question is now related to what the syllabus expects you to know. So let's begin. You should be able to see my screen. Can someone just confirm that they're seeing the screen and they're able to hear clearly in terms of the audio?
Yes, sir.
Okay, perfect. All right, good. So as I said, we're gonna just go through these questions, and as we go through, if there are questions, feel free to ask the questions. You can also utilize the chat feature. I will occasionally check the chat to see what the questions are. But if it's something of dire concern that you need immediate explanation or re-emphasis for, then you can use the mic, and I will take your questions. All right, so we're starting off with this question right here. This is from the 2010 paper, and it says here that a student connects the circuit in figure 1 below to investigate rectification using a single diode. Now, first of all, we are told that, okay, we have a circuit, and the aim of the circuit that the student constructed was to investigate rectification using a single diode. And as we're reading these questions, oftentimes we really want to make it a priority to aim to understand what the question is asking, number one, and also what information is enclosed within the question. Oh, this is 2010, right? So 2010. So yes, as I was saying, we want to be able to understand what the question is asking, and also try to get as much information from the question itself. So it says that they want to investigate rectification, right? So as we see this word right here, we should know, okay, that they're going to expect us to know what exactly is rectification. And we're told that it is done using a single diode, which is some key information, right? Now, we have our circuit right here. We have our power supply, or our voltage supply, and we see that we have this squiggly line feature. That's what I refer to it as, a squiggly line, which indicates that this is essentially some alternating current. So we have this alternating current source right here. We have our resistor, which is represented by R here. We have a switch indicated by this S, and then we have our diode. And then we have our output voltage that is going to be able to measure it from this section. Now, first thing that they say we need to do is to sketch V out, right? Sketch the V out against time graph when the switch is open. So again, we have to clearly understand what the question is saying. So it says we're to sketch a graph. Again, it says V out against T when the switch is open. So the switch right here would be open. So with the switch open, is this diode connected to the circuit?
No.
No, right? So the diode would not be connected to the circuit. So therefore, we're going to have our circuit essentially looking like this, from the power source through the resistor and then to V out. So basically this is our circuit. So we can assume that this portion of the circuit is non-existent. All right, let me just take that out. All right. So our diode is not connected. So therefore, since the diode is not connected, we're not going to have rectification taking place. And we should know that rectification is essentially when we take an alternating current signal and we convert it to direct current. So we take an alternating current signal and we convert it to direct current. That's the process of rectification. So let's see if we can sketch our graph now. So it says we're to sketch a graph of V out against T when the switch is open. So again, our diode is not connected. So therefore, we're not going to have rectification taking place. So since we have an AC source, right, at the input, we're going to get an AC signal measured at the output again because we don't have rectification taking place. So we can sketch that. So like that. And again, remember, an alternating signal, it changes direction over time. So we see it traveling, or it's being directed, it's flowing, sorry, in a positive direction. And then after some point, it changes direction and flows in the opposite direction, which we tend to refer to as negative. So in other words, this would be the positive direction. This would be the negative direction when the current is flowing in the positive direction. All right, so that's that for 1 mark. Now, next, it says we're to sketch the V out against time graph across diode D when the switch is closed. So in this case now, we're considering that the switch is closed. So with the switch closed now, like that, we can now consider that, okay, our diode is now connected in the circuit and we want to measure the V out across this diode. Now, since we have a single diode right here, we're going to get what we refer to as half-wave rectification. So let me just make a note that we're going to get a thing called half-wave rectification. All right, if I can spell that properly. That's essentially what we're going to sketch right here, half-wave rectification. So, with half-wave rectification, as it says, half-wave, we can always think of this as, okay, just half of the signal, right, is being rectified. So in other words, half of the signal is going to be converted to direct current. So we have our AC signal right there, AC signal, and we're going to send this into the diode. So this goes into the diode, and what we're going to see now is that the positive half of the cycle is going to be converted to direct current, and the negative half is going to be cut off. And the reason for that is we can consider for our diode, this would be our positive terminal, this would be the negative terminal. So wherever we see the bar on the diode symbol, that's the negative terminal. And the other side is going to be obviously the positive terminal. So in this case now, we can consider that our diode is in a forward bias configuration. So we're going to have the positive half of the cycle being rectified. And again, the reason why we can use a diode for this purpose is because a diode allows current to flow in one direction. All right? So a diode allows current to flow in one direction. Okay, do like this. All right. Anyways, don't like the pencil icon, but anyways, a diode allows current to flow in one direction only. So when we have the positive half of the cycle reaching the positive terminal, it's going to allow it to flow, right? But as soon as the negative half of the cycle appears right here, it's going to block it off. So as a result of that, we're going to get our output signal looking like this, right? No. We're going to have our output signal looking like this. So we're going to get to a positive side like that. Alright? Now as soon as the negative tries to flow, we're going to get a flat line, like so. And then we're going to get the other positive half. So as we see, just these two portions are actually converted to DC. The other portion is basically blocked off totally. All right. Are we good so far?
Yes, sir.
Okay. All right. Good work. All right. So let's continue again. No.
Sir,
Yes.
sir, is it half-wave rectification because there's only one diode?
Yes. Yes. So only when we have one diode, we facilitate half wave. And your syllabus only requires you to be exposed to the half wave rectification. There's also full wave, which involves 4 diode, but that's outside the scope of the syllabus. All right.
Okay, sir.
Yes. Now it says we're to sketch the VT graph across a battery power source. Now a battery provides DC, right, which is direct current, which flows in one direction. And since we're talking about a battery, we're going to see that the DC signal from the battery is going to be steady. So we can sketch just a straight line like that. Okay, so that's for the DC. Again, this is also DC. Right, note that this is also DC current, but this is a fluctuating DC because you see that it increases up to some maximum value, decreases, right, and then it continues after this portion. So this is a direct current, right, but again this would be a fluctuating DC current, while this right here would be a steady DC current. All right, now it says what is the
Oh,
symbol?
sir.
Yes,
Sir.
yes,
Is the case that all batteries are DC?
yes, all
Like
batteries are
stated.
DC. All batteries provide a DC current, right, or DC voltage. I mean, usually we use the terms current and voltage interchangeably when we're talking about AC, DC. All right, so what is the similarity in the voltage between 2 and 3? So what can we say about the similarity between the voltage between 2 and 3? What similarity?
They're both DC.
Right. So we can say simply they are both, I'm going to say DC voltage, right? They're both DC voltage, right? Or we could say they both flow in one direction, right? Could also mention that, which is a key characteristic of DC. All right, now it says, so how can you use a circuit in figure 1 to determine whether or not a semiconductor diode is defective? So how could we determine if this diode is defective?
The current is not passing through.
The current is not passing through, okay? But that wouldn't really
Doesn't change it from AC.
wouldn't change from AC to DC, okay? Right? Yes. But how could we check really if we have a DC or if we have DC or AC? Right? How could we check that? I mean, it might require us using additional equipment like maybe an oscilloscope to determine if it's converting the AC to DC. But if we go back up to something that I made mention of earlier, right? Notice what we said right here about the diode, if we can make this out clearly. What we say about the diode?
Current flow in one direction.
Right? Allows current
Allows current.
flow in one direction. So a diode, its function is to allow current to flow in one direction. So what we can do is we can set up our circuit, right? And we can, let's say we replace this AC signal with a DC source, right? Or a source that flows in one direction, right? And we maybe connect an ammeter in the circuit. So let us say let me just resketch the circuit. So we're going to have something like that. We're going to have our resistor, right? And let's say I put an ammeter here, like that. And again, we're going to have the switch close. We have the diode like that. So if we connect to our circuit like this, right? Again, we say that this is the positive and this is the negative, right? So let's say now we connect to our circuit like this. So for the battery also, this is also polarized. So this is positive and this is negative. So we have the positive connected to the positive, negative connected to the negative. And that is a legit confirmation, or in other words, that is a proper connection of the diode. The positive of the diode must be connected to the positive of the battery. Now in this case now, we're going to have a configuration known as forward bias. So the diode is going to be in forward bias, and as a result of that, we're going to have current flowing. So in other words, we're going to be able to get a reading on this ammeter. Right? So we're going to get a current flow, which is going to be detected on this ammeter. Okay?
So that's it.
Well, no, that's just part of it. Right? That's just part of it. So we could connect a circuit like this, right, with our diode in place, and let's say we get current flow this way. Now, let us say now that we basically turn around the diode, or we could turn around the power source, but let me just use the diode. So we change the diode orientation. So now we have the negative connected to the positive and the positive connected to the negative. Now in this arrangement, this current should not flow. So we should not have a current flow, right? So this current should not flow because again, the diode only allows current to flow in one direction. With me?
Yes, sir.
So then, if it is that when we do this experiment or this investigation, when we change the orientation of the diode, if it is that we are getting current flowing in both ways, it means that it means that the diode is faulty. Also, if no matter how we turn the diode, there is no current flow, then it is going to be faulty. So let me see if I can summarize that.
Yes, sir. So current to stop at the diode current to stop at.
Right, so there'll be no, because again this is negative, so no current will be able to flow across the diode. And there's a reason for that in terms of its construction, but again, this is outside of your syllabus. But let me just tell you basically what happens. When we connect it like this, think of like a small stream, right? Let's say a small stream, and you have the bank. Let's say this is the bank, let's say like a small river, right? And you're on this side, right? You can simply jump across when the stream is small. So when the stream is small, the diode is in forward bias. But when we now connect the diode in reverse bias, this stream becomes wider, right? So you're not going to be able to actually safely jump across. So that's basically what happens. But again, diode only allow currents to flow in one direction. In the forward bias, it will allow current to flow. And forward bias is when you have positive connected to positive. But if you now connect it in reverse bias, where we have positive connected to negative, no current will flow. Alright, so it says how can you use a circuit to that, okay? So we can say that the circuit or the diode, let's see, the orientation. And I guess first, since we would have changed the power source, let me just start with that. So let's say that the AC source could be replaced by a DC source, and the orientation of the diode changed to see if current flows in both directions, right? Both directions or not at all. Right, so we can simply, as I said, change the AC source to a DC and just change the orientation of the diode and then check to see if we have current flowing in both ways. Now, one of the things that we can be mindful of when we're answering questions like these, we can definitely sketch a diagram. So even if so just as I would have sketched a circuit right here, you can also sketch a circuit, right? In addition to what you would have stated here for your answer, just to show the examiner that, okay, you know what you're talking about, right? And let us say, even in terms of, how you would have described it, let us say that it's not completely clear to the examiner. At least the diagram, will be there to support what you are stating right here. Okay, all right, so hopefully that's clear for us. We continue with part B. And this one says that the truth table of a logic gate is shown below for inputs A and B and C and output C. Now it says state the type of logic gate. All right, so let's just kind of briefly look at logic gates. So we have this one right here, which kind of look like the diode. Say like this. So we have this. Anybody recognize what this gate is?
Yes, sir, it's a fuse diode.
It's a
Fuse diode.
fuse diode. So like it putting two devices into one, a fuse and a diode.
Yeah, a NOT gate.
Right, so this is a NOT gate. Right, so let me just sketch them quickly. So that's that. We have this one. Right, we also have this one. And we have these two as well. Right, hopefully that space can write them in. So we have the NOT gate at the top. We have this one. What gate is this one? Quickly.
OR gate.
R gate.
Right. Next one below.
And the
And right, and A and B. And this one is the NOR gate, and then this one will be the
NAND.
NAND. Okay, so these are our 5 basic logic gates. Now, how I like to think of logic gates, a NOT gate is also called an inverter, right? Also called an inverter. So whatever is present at the input, which is on the left you have the input and on the right you have the output. Whatever is at the input, it's going to invert it and provide that the output. Now in this case, since we have A and B as our inputs, we can ignore the NOT gate because the NOT gate only have a single input, so it's not going to be suitable for this table. Right, so we can look at our other gates. Now for the OR gate, I like to think of it as performing addition. The AND gate basically does multiplication, M-U-L-T, multiplication. So whatever is at the input for the OR gate, we can just add them, and that's going to determine our output. For the AND gate, whatever is at the input, we can multiply them, and then that's going to give us our output. I'm going to talk about the NOR and the NAND shortly. So anyways, let's see what we have right here. So we have 0, 0, right? 0 times 0. Well, let's do the addition first. 0 plus 0 would give us 0, right? So that's not the OR gate, because again, the OR gate, we would have to add these, and then that's going to give us our output. If we check the AND gate now, we can say 0 times 0 should give us 0. Here we have a 1, so therefore this is not the AND gate. So let's look at our NOR gate then now. So the NOR gate, we can think of the NOR gate as just an OR gate. So let's say we have that, like an OR gate like that. Sorry, let me move that. So the NOR gate is as if we have an OR gate and we connect to it a NOT gate. So that's the basic idea behind the NOR gate. Similarly, the NAND gate is as if we have an AND gate and we connect to it, to the output of it, a NOT gate as such. So then, we can now use that to help us to determine the type of logic gate. And again, if we know the different truth tables, because sometimes you can study the truth tables for the respective gates, but here we're just demonstrating how you can just reasonably go through and determine which gate would be associated with this truth table. So anyways, let's say now, so we say 0 plus 0 we're going to get 0, right? So 0 plus 0 should give us 0 if we add them, right? And if we pass it through the NOT gate, if we consider the NOR gate, we should get a 1. So that is true. But let's check the other bits just to make sure. I check the other inputs to make sure.
So you have a set number of people who can join?
I think it's cut off at 100 maybe. Yeah, I think we cut off at 100. I wanted to open up a YouTube thing, but it wasn't working out for me. All right. So unfortunately, if we stop at, we max out at 100, then so okay, so let's continue. So we said no, we're gonna try this now for the NOR gate. So we're gonna say 0 plus 1 should give us 1, right? And then we're gonna pass that through the NOT gate, so it should give us 0. So therefore now we can eliminate our NOR gate. So the only one left is the NAND gate. So we can say by default this is going to be our NAND gate. But again, we can verify it. So 0 times 0 would give you a 0. Pass that through a NOT gate, you're going to get a 1. 0 times 1 would give you a 0. Pass that through a NOT gate, you get a 1. 1 times 0, also 0. Pass that through the NOT gate, you're going to get 1. 1 times 1 is 1. Pass that through the NOT gate, you're going to get 0. So hopefully that makes sense to us, and hopefully as we go through a while, it kind of gives us a recap. Yes, question?
So the NOT gate represents a 1?
No, the NOT gate is an inverter. So whatever is present at the input, so if we have a 0 right here, you're going to get a 1. Right? And if you have a 1 right here, you're going to get a 0. So whatever is present right here, it gives you the opposite.
Okay, so it's always 1 and 0?
Yes, always 1 and 0. When we look at logic gates, the input, output is always 1 or 0. Okay?
Sure, question.
Yes, go.
Sure, so notice that on the NOT gate, one line, they like the bucket.
Right.
And everything is up to.
Right. Yes, it does. Good question. So the NOT gate, it only have a single input. So NOT gate has one input and one output. You're always going to have one output, right? Always have one output for whatever gate that you have. But for the NOT gate, it's the only one that only has one input.
So is that why we use the NAND instead of NOT?
Yes. Well, not only that, not only that. It has to do with, so the fact that, we have two inputs. These are our inputs right here. The fact that we have two inputs, then we have to look strictly at one of the gates that have two inputs, which could be the OR and the NOR or the NAND. Now, what we did now is we look at our inputs. So again, as I said, for the OR gate, think of addition. And for the AND gate, think of multiplication. Now, we saw where for the OR gate, if we say 0 plus 0, that should give us a 0, right? Which we get a 1 right here, so that is not true. So we can eliminate the OR gate. The AND gate now, that's multiplication. We say 0 times 0 should give us 0, but we're seeing a 1 at the output. So it means that, okay, this was not the gate. So it's down to the NOR or the NAND. Now, we saw for our first input, we say 0 plus 0 gives you 0, right? And again, the NOR gate is a OR gate with a NOT gate. So we have 0, 0 right here. We're going to get 0. But since we have 0 at the input of this NOT gate, we should get a 1. Now, we have 0, 1. Let me change the color. Hopefully this doesn't get too messy for us. We have 0, 1 at the input. 0, 1, we add them, we should get a 1. Now this one goes into the NOT gate, should give us a 0. But we see we have a 1 right here. So as I said, we can also eliminate that this truth table is for the NOR gate. And then by default, it left us the NAND gate. And it verifies, if we show it. Okay? Good? Are we good?
Something like that.
Something like that. All right. So let's see now. So that's that. Let's continue. Okay, so we have this thing now for this truth table. So hopefully this will give us an opportunity to cement our understanding of what we just discussed a while ago with regards to the inputs and the outputs of the logic gates. All right, so it says complete the truth table for the following logic circuit. So this gate at the top right here, this which gate is this right here?
Or gate.
All right, so this would be the OR gate, and this one right here would be the
Not
Gate.
gate.
right not, and then this one is the
And gate.
and, right? So these are our 3 gates. Now we're to complete this truth table. Now what we will have to do is we'll have to look at the output. So we have each output. So we have the outputs C, D, right? Outputs C and D. Output C is from this OR gate, while output D is from this NOT gate. We also have an output E, which is from this AND gate. Now notice also that this AND gate is connected to C and D, which are essentially outputs for this OR gate and this NOT gate. So while these are outputs, they also serve as what we refer to as secondary inputs. And secondary input because it is connected to the input of this logic gate right here, which is an AND gate. So let's look at each in sequence, because that is how it's going to make sense to us. Because sometimes, we see a question like this and we might think, okay, we don't know what to do. But what we need to do is to really take the time to break the question down into parts. And that is why, you have part A, part B, and so on for each question. So anyways, let's look at the output C. So output C is connected to this OR gate. So again, with OR, we can consider addition. So that is why we have 0 plus 0 gives you 0. 0 plus 1 should give you a 1. 1 plus 0 should give you a
1.
1. And then we have 1 plus 1 should give you a right? Okay, so your person says 2, right? So because we're looking at binary, we don't consider 2 is either 1 or 0. So even though the addition allows us to get 2, it's really 1 plus what we call a carry. So we can just record this as just simply a 1. All right, next one now. So D is the output of this NOT gate. Right, so D is the output of the NOT gate. And the input for the NOT gate is from B. So we're using B as the input and the output is D. So when B is 0, D is 1, because D again is the output for the NOT gate. When B is 1, D is going to be what? 0, right? And when B is 0, just like this, we're going to get 1 like that. Right? Now E now is the output of this AND gate, which is connected to C and D. So when we're determining the output of E, we have to look at C and D. So let me change color again. Let's use black. So again, AND gate, so we consider multiplication. So we can say 1 times 0 should give us a 0. 1 times 1 should give us a 1. And then 1 times 0 gives you a 0. And that's our table now completed. All right, any question on this?
No, sir.
Okay, all right, good work. So, okay, good. All right, so now we can continue. All right, so here we have a question right here. So this question says, with reference to the diagram of a simple DC motor shown in figure 2, explain how this motor works. All right, so here we have this question and we need to explain precisely how this motor works. Now, in order for us to be able to explain how this motor works, we need to be aware of some key concepts. So we need to be aware of a thing called the motor rule, right? And we need to be aware of well, the motor rule, which is also referred to as Fleming's left-hand rule. So let me say motor rule or Fleming's Fleming's, in terms of this, 2m, 1m. So Fleming's left hand rule. And we also need to be aware of a thing called, well, firstly, let me put this at the top, the motor effect. So we need to be aware of the motor effect, and we need to be aware of the motor rule. Now, the motor effect, let me just make some summary on this. Let me see if I have any more space. All right, so the space is kind of limited. So please bear with me. I think maybe what I should do is really bring this over to the next screen. Anyways, the motor effect. Right, so the motor effect basically says that if a current carrying conductor is in a magnetic field, it experiences a force. All right, so if a current carrying conductor is in a magnetic field, it's going to experience a force. So for instance, just to illustrate this or to demonstrate this, so let us say we have a magnetic field. So we have two bar magnets. Let's say we have a north pole and we have a south pole, like that. So we have these two bar magnets, and in between them we're going to have a magnetic field. Let me represent that magnetic field. And the magnetic field is always directed from north to south. So let me put that in. Choose this color, which is light. So the magnetic field is going to go from north to south. Say something like that. So between these bar magnets, we're going to have our magnetic field that is directed from north to south. Now what we're saying now is that if we... Yes.
We're going to take converge. Let's say converge to south, like diverge from north and converge to south.
Does it?
No, that's what I'm asking.
I'm hearing the question, I'm hearing the speaking, but I'm not hearing it clearly. I hear a convert. So I want you to just repeat for me.
I'm asking if the magnetic field diverges from the north and converges to the south.
Diverges from the north and converges to the south. Well, I guess you could look at it from that point of view, where it spreads out from the north and then converge towards the south, because in truth and in fact, we don't only have magnetic field going straight across, we also have them going out into space, right? And also, so I guess yes, you could say, okay, they diverge from the north and they converge towards the south, right? You could also say that as well.
So isn't that called stray magnetic fields?
Yes, they refer to as stray magnetic fields, right? That stray off into space. All right, let me clear that out. So we have our magnetic field like that from north to south, and if we now have a conductor carrying a current, so let's say we have a conductor, let's say like that. I'm just going to show, so this is like a section of the conductor, for instance, and it is carrying a current along its length. Now let us say that we place that conductor within the magnetic field, right, such that the conductor, let's say the conductor is placed like that within the field, and it's carrying a current. Let us say it's carrying a current into the page, right? So again, we take this conductor and we basically push it through the screen of the computer. So the current is moving along its length and it's moving away from us. Now what we're saying now is that in this configuration right here, we're going to see that this conductor is going to experience a force. So there's going to be a force on this conductor right here. All right, are we okay with that so far?
Yes, sir.
All right, so there's going to be a force on the conductor. Now we can determine the force on the conductor by considering the magnetic field lines, right, between the north and the south pole, and we can also consider the fact that, okay, since this is a current carrying conductor, there's going to be a magnetic field associated with it. Now, let me not go into that detail in terms of this question right here, but we can see also that we can determine the force on this conductor by considering Fleming's left-hand rule, which is also known as
Somebody
the
said nasty.
not seeing
Yeah.
seeing the screen now.
No, I mean like them not catch it.
Oh, okay. All right, okay. All right. So what we're saying is that when this conductor is placed within this magnetic field, it's going to experience a force. That's what the motor rule, sorry, the motor effect says. So once we have a current carrying conductor in a magnetic field, it's going to experience a force. Now that force is due to, so if you think about it this way, so we all know, okay, let's say we have a magnet right here. Let's say this is the north, and let's say we have I mean just like what we have right here. So we have a south pole right. Let's say we have two bar magnets. We have the north pole of this magnet here and the south pole of this magnet right here. Now we know that, okay, if we place these two magnets in close proximity, what's going to happen to them?
So it's supposed to attract.
Each other.
You're going to attract each other, right? And that attraction is due to a force between the two magnets, and the force is essentially due to the magnetic field lines. So again, we know that, okay, if we have a north pole and a south pole of two bar magnets, then there's going to be a force, and the force is due to the fact that we have, again, so if we were to think of and again, I'm trying not much as possible not to go into too much details, but let's just do it for the sake of our understanding. So we have a north pole right here. As we said, they diverge from the north pole and they converge at the south pole. That's the idea we just mentioned a short while ago. So we have these field lines. Now once the bar magnets are close enough, what we're going to see now is that these field lines are going to interact. So because these field lines want to go outward and these want to go inward, what we're going to see is that there's going to be an interaction, and we're going to get basically this pattern being formed, which now creates a force of attraction. So the north pole is going to be attracted to the south pole, just as how the south pole is being attracted to the north pole. So what we see now is that once there's field lines involved, right, around a magnetic material, once they interact, they're going to exert a force on each other. All right, can we accept that?
Yes,
right. Can we accept that? Okay. Now, in terms of a current carrying conductor, when we have a current carrying conductor, there's a magnetic field associated with it. Right? So let me just kind of summarize that. So again, hopefully this doesn't get too messy for us. I really wish I had more space. A current carrying conductor has a magnetic field associated. Right? So a current carrying conductor has a magnetic field associated. So let me just do a little sketch of this. So let's say we have a current carrying conductor like that. Let's say this one is just like what we said over here. So this is going into the page. So we can put an X like that. And we're going to consider one like this now, which is coming out of the page. Now, to determine the direction, and first of all, the direction of the magnetic field is going to be in the form of concentric circles. So the first thing I can do is to draw some circles around these. So I'll draw two of them. So these circles basically represent the magnetic field around our conductors. And as I'm going through, if anything is not clear, let me know. Right? Because again, we might be going through quite a lot in terms of just for us to really understand. Because again, is this really we want to get to? But I want us to fairly have some background knowledge in terms of how we can explain this. So again, as I'm going through, if persons have questions, let me know so I can stop and explain where persons are having difficulties. Okay, so what we're saying is that whenever a current carrying conductor, the magnetic field is going to look like circles. That's it. That's the bottom line. The magnetic field is going to look like circles. Now, the magnetic field is going to have an associated direction with it. Right? So while we represent the magnetic field as circles, the circles are going to be in a particular direction. Now, for this conductor carrying the current into the page, what we're going to see now is that if we take into, and again, as I said, we're going to talk about a lot of things, just to really get up to it. But essentially, for us to determine the direction of the direction of the magnetic field around this current carrying conductor, we take on a thing known as the right hand grip rule. Right, let me switch screen because I really think I'm kind of getting messy with this. So let me how do I change screen again? Oh, let me do that. All right. Okay. Where am I right here? Okay. All right. So let's get ourselves up to speed now. So again, we had something looking like this. And again, we're trying to explain the motor effect. So we had our magnetic field, and you guys are seeing the screen. Can someone just confirm for me?
Yes, sir.
Okay, so we have our magnetic field like that. Yes, good. So this was north, that was south, and we have our conductor, say like that, because we want to be able to see the conductor, so I'm going to place it right there. So we have our conductor like that. Now what we're saying now is that when we have a conductor carrying a current, let's say like that, and again this one was going into the page, and we have this one right here coming out of the page. So the X means that the current is moving away, the dot means that the current is coming towards us. So we said that the magnetic field is going to be like circles, right? Circles. Right? And if we want to be a little more technical, we can say concentric circles. So we have these circles like that. So like so, and like so. Now to determine the direction of the magnetic field around this current carrying conductor, we use what we call the right hand grip rule. Right hand grip rule. And the right hand grip rule is simply exactly what it says. Right hand, take our right hand and we grip the conductor. Alright? So with the right hand grip rule, we take our right hand and we're going to, so imagine that you're gripping this conductor. Right? So we have these two conductors, and again, this is just the cross section of the conductor. So we can imagine that the conductor continues like that into the screen. Right? Fair enough?
Yes, sir.
Right? So the conductor continues into the screen. So let's imagine that we're going to grip that conductor with our right hand, such that we're going to have our thumb sticking out. So again, so imagine that you're giving somebody a thumbs up. Right? That's another way we can visualize it. So imagine you're giving somebody a thumbs up. So your thumb is going to be sticking up, and your other fingers are going to basically form like a fist. So what we do now with the right hand grip rule, we grip the conductor and we ensure that the thumb is pointing in the direction of the current. So in this case now, since the current is going into the screen, because we have the X right there, the current is going into the screen, so our thumb is going to point into the screen. Alright, can we make sense of that?
Yes, sir.
So basically what we're going to have is we're going to have our thumb going something like that, and then your fingers are going to curl, if I can you know, draw it, but you know, something like that, right? Not a good drawing, but you know, you're gonna have something like that. Make sense? So we have this taking place. Now we see that our fingers are curling in this direction. So since the fingers are curling in this direction, what it means is that the magnetic field is also going to be in that same direction. So since the fingers curl in a clockwise direction, then the magnetic field is going to also be in a clockwise direction. Is that good?
Yes, sir.
Now, once we would have done this for the one going into, then if it's coming out, what would be the direction of the magnetic field?
Anti-clockwise.
Right, anti-clockwise. It's going to be the opposite, like that. And again, we can use the right hand gripper. So in this case now, we're going to have our thumb pointing out. So with your thumb pointing out, so your thumb is going to be pointing this direction, and then your fingers are going to curl something like so, right? Kind of, again, poor drawing, but hopefully we get the idea, right? Okay, so that's what we see. Now, with that being the case now, because there's a magnetic field around this current carrying conductor, and there's a magnetic field between these two bar magnets, those magnetic fields are going to, or the two magnetic fields are going to interact. So the magnetic field of the bar magnet and the magnetic field of the wire or the conductor will interact. And as a result, there's going to be a force on the conductor. Right? Yes, right? So as a result of the magnetic fields interacting, there's going to be a force. So we said that this was carrying current into the page, so we should expect the field should be, this is what, again, clockwise direction. So let me just try redraw this. So we're going to have something like that. And again, this is just allowing us to see the motor effect. So that's north, that's south. We have our conductor like this. Now it's carrying current into the page. So we have a magnetic field. I'm just going to draw one of them. Just going to draw one. So we have the magnetic field. Again, we're going to have many of these, but I'm just showing one. So we have that taking place. Now, in between the bar magnets, we're going to have the magnetic field directed from north to south. So let's see if we can show that now. So we're going to have this one going from north to south, and we're going to have this one going from north to south. Now, these field lines, they are essentially lines of force. So we can take into consideration that, okay, when these lines of force interact, they're going to add vectorially. So think of forces in the same direction. When they add together, right, they're going to, we're simply going to take the sum. But if they're in the opposite direction, we take the difference. So what we can consider then now is that, let's say we take the difference of these two and they're going to cancel out each other. So essentially what we have now is that these are going to cancel out. Hopefully we can see that. Right? These are going to cancel out. And we're going to have, right, good. And then we're going to have the field, these field lines at the top right here. Now, what we see now is that at the top, there's going to be a greater force than at the bottom of the conductor. So since we have a greater force at the top of the conductor, right, than at the bottom, what we're going to see therefore now is that this conductor is going to move downward due to that force. The ones in the same direction, they add, and the ones in opposite direction, they cancel out.
So it's something like vectors.
Yeah, man, just like vectors, yes. Right, because there are lines of force which are essentially vector quantities.
Yeah, and the interference, something like the sound wave.
Right, exactly. Like when they're out of phase, you know, they cancel off. Right. So that's what we see. So the conductor is going to move downward. And again, we can show this again by using Fleming's left hand rule. But we'll just by considering the field lines, show that okay, this conductor is going to get a force and it's going to be force downward. So as a result of that now, this conductor is going to tend to move down. And again, we can verify this using Fleming's 1M, Fleming's left-hand rule. So with Fleming's left-hand rule, we have to align our fingers like this. So your thumb, your index finger, or your first finger, and then your second finger or your middle finger. Right? So index or first finger. Alright, so I'm kind of going at this quickly, so bear with me. We're going to really go back into details with this in terms of when we look at the thing with the motor thing. Alright, so we have that. So again, we take our left hand, 3 fingers like this, and they should be at right angles to each other. So in this case now, the index finger, again, if I'm going fast, I know I'm going fast, so just bear with me, please. So the first finger is the field, second finger is for the current, right? I realize there's a question. Is there a question somewhere? Okay. All right, so first finger is the field, second finger is the current, and the thumb is for the force. So essentially, what we need to do is we need to align our index finger in the direction of the field. So the field is going to the right from north to south, right? So our index finger must point from north to south. So we take our left hand, point the index finger north to south. Now the second finger represents the current. The current is going into the page. So we might have to rotate our left hand so that our second finger can point into the page and the index finger point from north to south. And what we see now is that the thumb points down, which confirms to us that the force is going to be downward. Okay?
Yes, sir.
All right. Again, a lot of things to consider, right? But hopefully, as we go through and we show in terms of the demonstration, we can confirm what we would have explained right here. All right. So let's see now. So with the question, let me see if I can get back to this. All right. All right. Let me see if I can somehow get this in. Let me try a thing. All right. Let me try to include. I'm just gonna copy this and paste it here. Let's see if this will work. Let's see if it works. Okay, yes. All right, good. So this was our motor or DC motor, and we're going to, with reference to this, explain how the DC motor actually works. All right, so with our DC motor, notice that we have these 2 bar magnets, right? So we have the North Pole and we have the South Pole, and we have a single loop that is inside or between the 2 bar magnets, and they're connected to, we see that, okay, that they say that this is a commutator right here, so it's connected to this commutator, carbon brush, and we have this external circuit. And in the external circuit, we have a battery, we have a rheostat, which is essentially a variable resistor, and we have a switch right here. All right. Now, we're going to now explain how this works. So again, the principle of the working of a DC motor relies on our ability to understand the motor effect as well as the motor rule. Because again, the motor effect says that once there's a current carrying conductor in a magnetic field, it's going to experience a force. So in this case now, when we close the switch right here, we're going to have current, let's say, and for this particular discussion, we're going to consider the movement of positive charges. So this is the positive terminal, this is the negative terminal. So we're going to consider the movement of positive charges. So we're going to have a current flow in this direction. So the current is going to flow from the battery through this carbon brush, right, which is making contact with the commutator, right, and then it's going to now go into the loop, because the loop is actually connected to our commutator right here. Now that current is going to continue through side AB as what is indicated by the arrow, and then it's going to continue around, okay, around the circuit. Are we comfortable with that?
Yes, sir.
Yes, sir. Now, it says, well, based on the diagram right here, it shows an arrow to say that, okay, this is going to rotate anti-clockwise. So let's now see if we can verify this to be anti-clockwise, and we're going to also describe how this really works. So let me just explain first, and then I will kind of summarize what I would have stated. All right, so let's consider now that current is flowing inwards along AB. So again, if I were to I'm just gonna make a one-dimensional representation. So let's say this is the North Pole, this is the South Pole, like that. We're going to have our loop. So let's look at just side AB and side CD. So we can represent side AB, let's say like a circle like that, and side CD also like a circle. So again, it's like we're looking at it you know, sideways. Are we okay with that?
Yes, sir.
Yes, sir.
All right. Now on AB, the current is going in, so we can show that with an X like that. While on this side, the current is coming out based on the arrow, so we can show that like a dot. Now, what we see now is that once that occurs on side AB, again, the current is going in, right? And again, we can use Fleming's left-hand rule. So the current is going in, the field is from north to south. So this side of the conductor is going to feel a downward force. So that's the force on this side going downward. All right? If anybody is having any challenges so far, let me know. All right? So seems like we're good. So on this side now, which is side AB, there's going to be a downward force. While on CD, we're going to get an upward force again, because if you use Fleming's left-hand rule. So again, the field is from north to south. The current is coming out towards us. So our second finger points towards us, and the thumb will point upward. So we're going to have a force upward like that. So what we see now is that AB experiences a downward force, but CD experiences an upward force. And those two forces now are going to create what we refer to now as a couple. So we have a downward force. So it's like you know, you have a seesaw, you're pushing one side down and you're pushing the other side up. It's going to cause it to rotate. So our loop then now will now start to rotate. So as the current is flowing through, we're going to get this motion taking place. Alright, so we're now essentially now taking the electrical energy from the battery and creating motion, which is essentially what a motor does. Okay?
Yes, sir.
Yes, sir. Yes, sir.
Alright, so now as that continue to happen, notice that again, in order for current to reach the loop, it must flow through the commutator, right, and the carbon brush, as well as the external circuit. Now notice that, I don't know if you're able to see, but notice on the commutator right here, it's not a complete complete loop, right? So it is actually look something like this. I can draw it, right? Kind of poor drawing, but look something like this. So there's basically a gap, right? There's a gap right here, right? So there's a gap, and there's a reason for that. So as this starts to rotate, right, at some point it's going to, the carbon brush is going to be in between the space right here. So in other words, there's going to be no electrical contact between the external circuit and the loop because of the gap right there. Now at that point now, what we're going to see now is that because the loop was actually rotating and it has some inertia, is going to continue to move under inertia. It's going to continue to move, and what we're going to see essentially is that we're going to have these two commutator rings basically switching places. So this commutator ring that is connected to AB is going to move over to this carbon brush labeled Y, while this commutator ring is going to move over to this carbon brush labeled X. So hopefully we can see that. But again, if there are questions, let me know. All right, let's summarize all of that. So we're going to say now that as current flows from the battery, right, and we can say from the positive terminal of the battery towards the carbon brush, the current enters the loop via the commutator rings, and again they're called split ring commutator, right? Current, let's kind of see what we have so far. Towards the carbon brush, the current enters the loop via the via the split ring commutator, let's say along side AB. Right? Now, side AB, therefore, now experiences a force, and that force is going to be in which direction?
So,
force on AB is going to be
downward.
right? Downward. Side AB experiences a downward force. Right? And again, we can say based on Fleming's left hand rule. Now, as the current continues around the loop and it is now exiting, it's now exiting it's now what am I saying? It's now coming out of the page along CD. Then CD is going to experience an upward force. Now side CD experiences an upward force, right, which creates a couple of forces, right, causing the loop to rotate. All right. So because you're pushing side AB down and side CD up, it's going to cause the loop to rotate. Now the loop continues to rotate until the carbon brush a second. Give me a second, please. Give me a second, please. I'm having some technical issues. Okay. All right. The loop continues to rotate until the carbon brush lose contact with the split rings. All right. But due to inertia, the loop continues to rotate. All right. It's going to continue to rotate under inertia. Now, what we see now, as I said, so if we go back up to our diagram, so if I somehow kind of color this in so we can keep track of it. So that's red right there. This one I'm going to color it blue. Right. Need to color in between the lines. Anyways, so we have the two what is called again? Split rings commutators. So we have our two split ring commutators. This red one is connected to AB and this blue one is connected to CD. So what we're saying now is that as it starts to rotate, it's going to continue rotating because there's a current flowing through the conductor, which causes a force to be exerted on the conductor, causing it to rotate anti-clockwise as we would have shown earlier. Now, what we see now is that at some point, the carbon brush is going to lose contact with the split rings. Because again, we can imagine that this split ring, it's actually connected to the loop. So it actually rotates. This side rotates with the loop right here. Similarly, this side is going to rotate with this loop. So if this is now rotating anti-clockwise, as what the arrow shows right here, what we're going to see now is that we're going to reach a point where the carbon brush is going to basically be in between these 2 points. In other words, if I were to sketch this out, so we're going to have our red carbon brush is going to be on this side, and the blue one is going to be like this. And again, we have our carbon brush, which is, say, like that, right? Something like that, and this one, right? Something like that. Right, you guys can follow what I'm saying?
Yes, sir.
Right? So what we see now is that at this point, the carbon brush loses contact with the split ring, so therefore there's going to be no current. Now in this arrangement, our loop is going to look something like that. Again, forgive me with the drawing, right? Loop is going to look something like that. So the loop is going to basically be vertical within the field. Now, once that occurs, I said, again, it was moving anti-clockwise, but due to its inertia, it's going to continue to move. So what we're going to see now, essentially, if I can let that stay right there, what we're going to see now, again, we're going to have this moving over slightly. So we're going to have the red one, sorry, the blue one looking something like that, and the red one is going to look something like so. Right, and again we have our carbon brushes, so we're going to see now that this one will now start to make contact with this carbon brush, and this one will start to make contact right there, right? So now this now causes now us to be able to re-establish electrical contact, right? This causes us to re-establish electrical contact. But notice what happens. The red, again mixing up the colors, the blue split ring is now on the left hand side, while the red one is now on the right hand side. You see that?
Yes, sir.
Right? Now, as a result of that, now what we're going to see now is that the side CD is now going to be on this side, and side AB is now going to be on this side. But again, because we have current flowing from the positive terminal, right, and it's going to be going in on this side. So on whatever side of the loop is on this side, the current is always going to flow inward on that side. So what we see now is that CD is now over this side. So the current is now going into CD, and the current is coming out of AB when it's on this side. Now, once that happens, it's going to ensure that we maintain that, okay, on this side, the force is downward, and on this side, the force is upward, so the system can continue to rotate in an anti-clockwise direction. Any question?
No, sir.
Right. So let me add some more to that. Add some more writing to this down here.
Can we explain
Yes.
previously?
Okay, so what we're saying now is that once we're in this position, we have no electrical contact between the carbon brush, which is carrying the current, and the split ring, because again, the carbon brush is in between the gap. So this will have no current flowing through it, but due to its inertia, right? So in other words, like let us say somebody trip your foot while you're walking. You're gonna continue falling downward, right? You're not going to stop midway, even though the person move them foot until they're sorry and all that. It's still going to move forward because of inertia. So the same thing happened right here. So it was moving originally, but due to its inertia, it continues rotating. So as it continues moving now, we see that the red side of the split ring is now connected to the left carbon brush, while the red, again this is blue, the blue split ring is connected to the left carbon brush, and the red split ring is now connected to the right carbon brush. So what we see now essentially is that sides AB and CD, they basically switch places. Now once that occurs now, on side CD, instead of the current coming out, the current is now going to be going inward. Right? Because on this side, you want the current to keep on going in, and you want the current to come out on this side so that you can maintain this action right here of having the system rotate anti-clockwise.
Also,
Okay.
when the upward force turn over, it's like it turn downward when you go on the next side.
Right.
AMC.
Okay. So let's say we want to add some more to this now. So it continues to rotate under inertia. Right. Now this causes the, sorry, again this is bad writing, the current in each loop, sorry, not each loop, but each side of the loop to reverse, thus maintaining continued or continuous anti-clockwise rotation. Right? So it's the action of the split ring that allows us to have continuous rotation in one direction. Right? Because if it is that we do not have that split ring, what we're going to see is that the loop, if I were to just represent it as a bar, the loop will just, let's say, rotate like that. So it's going to like swing to the left a bit, then it's going to swing to the right. So it's going to, so this side go down, this side go up for a moment, then this one go down and this one go up. So it's like it's going to oscillate, like if you have how can I say if you tie a string to a ruler and you kind of tap one side, it just kind of bounce up and down. That's basically what we're going to happen, but that's not going to be useful in terms of any device. For instance, if you have a DC fan, you want it to rotate, you don't want it to go back and forth, because as I said, it's not going to be a very effective force. All right, so that's all of that. Force to explain all of that in terms of how that works. Any question?
Sir.
Yes.
Okay, so sir, the motor would be going anti-clockwise because for the one going into the plate, the force would be acting down, and for the one coming out of it, which is CD, it has the
Yes.
upward force, so that would make it go anti-clockwise. And say when the
Right.
split ring rotate and goes on the other side, it continue to go into that direction because AB is still going into the page and DC is coming out.
No, AB is going to be coming out of the page, right? Because side AB is now over this side.
Also said that would make it continue to go up and down.
Right, exactly. Exactly. All right. So that's what we see. All right. So let me go back to the main screen. All right. How do I write this again? I need to go here and then go here. No, right here. All right. So as I said, hopefully we can appreciate that. Okay. And it says now give the purpose of the commutator. So what's the purpose of the commutator? You mentioned it a while ago. What would be the purpose of the commutator? Anyone? No one?
Say to help maintain the loop.
Kind of. Well, to help maintain rotation, right? So the commutator, its purpose is to ensure the direction of the current in each side of the loop is maintained, right? Therefore, ensuring continued rotation. Right? So the split ring ensure that, okay, on this side the current is always coming out, while on this side the current is always going in. Right? So once side AB comes over, the split ring is going to ensure that, okay, the direction of the current is now coming out, because again on this side they always want current to come out, while on this side they always want the current to go in.
So, sir, we don't have to explain how the commutator works exactly.
No, it just says give the purpose.
Okay.
Right, so the purpose is for it to maintain continuous rotation. So we want the current in each side to be maintained. Right, since I'm saying each side of the loop, right, you want to say reverse, because I'm relating it to the loop itself and not necessarily the magnet. So each side of the loop is reversed. It's current in each side of the loop is reversed. So again, once AB goes over this side, the current should come out, and CD go over here, current must go in. So the current is going to be reversed, and that's going to cause us to maintain rotation. All right, so that's that for the essay portion. All right, and again, the key thing with this, we have to talk about how the loop rotates. We have to talk about what consideration we take in terms of determining why the loop rotates. We have to explain the purpose of the components, so like the commutator, sorry, the carbon brush and the commutator. We have to mention that in our discussion. All right, next one now says a 24 volts DC motor was used to lift a small appliance of mass 25 kg from the ground to the second floor of a multi-story car park. The floor is 30 meters above the ground. The motor operating at 100% efficiency works at a steady rate and takes 5 seconds to complete the activity. Calculate the power provided by the motor. Alright, so how can we find the power provided by the motor? How could you find the power provided by the motor?
Share the work or energy over time.
Right, energy over time. Okay, so let's see what we have now for this thing. It says we know that, okay, we have a 24-volt supply. We have the mass right there, and we know that it takes 5 seconds to complete the activity. Now it says we need to find the power. So we said that power is energy over time, which is true, right? Energy over time. But in this case now, let's see what we have. So we know the mass, right? We know that the building is 30 meters above the ground, so that's going to be the distance that it actually moves, and we know that it takes 5 seconds. So since power is equal to energy divided by time, since we know the mass or we know the distance traveled, we can use that to find the work done or the energy, right? So we can consider that, okay, when the appliance is 30 meters above the ground, it's going to have some energy stored up, right, which we can consider to be gravitational potential energy. So we can say that our gravitational potential energy, right, is going to be equal to mgh, and we can really say the change in gravitational potential energy is equal to mg delta h, where the m is 25, where the m is, oh sorry, the m is 25 kilogram. G, always giving us G right here, so we can always look out for that on the paper. It's 10 newtons per kilogram. And the change in height, it's 30 meters above the ground, so it's going to change from 0 to 30, so the change in height is just going to be 30 meters. We can do the calculation with that, so that's like 7,500, if I did it correct. I'm going to confirm the answer for this one.
Yes, sir. 7,500.
Right, so 7,500, and this would be joule. Right. Notice also that we could have used a formula where we say that the work done is equal to the force times the displacement. Now, since it says that it's at a steady rate, we can assume that the weight of the object is going to be equal to the force required to lift it upward. So we can find the weight of this. So 25 times 10 would give you 250, and in the meter, or the displacement is 30, so we also get the 7,500 work done, so it's going to be joule. So we get that right there. Now we can find the energy, not the energy, the power I should say, by saying that power is equal to the energy over the time. Its energy is 7500 joule, and the time is 5 seconds. Right, so that's going to give us something like that. Right, confirm if I saw it go.
Yes, sir.
Right, good. So 1500 watts, and that's the power of the motor. Now it says we need to calculate the current drawn from the DC supply. So we can calculate power using this formula right here. But when we look at electrical power, we can also find electrical power by using the formula where we say that P is equal to I times V. So we know the V, that's given right there. We just found P, right, a while ago. So we can make I the subject, so we get I is equal to P over V, transposed by dividing both sides by V. So P is 1500, that's watts, and V is 24 volts, right? So 24 volts, and they're just telling us that this is DC, so this is not a part of the unit. So we put 24 volts right there, and then we divide that by that, and we should be able to get to our answer.
So 62.5 amps.
62 like that, 0.5, make that a little better. So 62.5, and this would be amperes. Right, so a lot of current. So 62.5 amperes. Now it says that if the power required to lift the appliance was greater, what effect would this have on the value of the current? So if the power required was greater, right, what effect would that have on the current? What can we say? And it says assume the voltage is constant. What can we
The current
say? What effect will it have? Current would
Increase.
increase, right? The current is going to increase, and it makes sense because if this goes up to, let us say, 3,000, this is going to double, right? So we can say that the current would increase, right? So the current would increase. All right, so that's good for us.
Yes, sir.
All right, so let's roll again. All right, so
Sir,
next
sir,
question
you
now
can go back a
says
little, please.
yes.
I want to take a screenshot.
All right.
Can move on now.
Okay, all right, good. All right. Okay, so let's see this now. So next question now says that and that question was from 2010. This one is 2011. Now this one says that figure 1 shows a simple cell connected to a circuit. So we have this cell which consists of dilute sulfuric acid, right? We have a switch right there, and we have a bulb, and we have some wires, copper wire, they say, that connect to everything. Now it says, how does the flow of current within the simple cell differ from that in copper wire? Now, for persons who do chemistry, right, we said that, okay, we have dilute sulfuric acid. Now, this sulfuric acid is in solution, right? It's in solution. So what we're going to see now is that we're going to have positive ions as well as negative ions that are going to be disassociated, right, in our solution of dilute sulfuric acid. Now, what we see now is that we have these two electrodes right here. We have a positive electrode and we have a negative electrode. So what we're going to see now is that we're going to have the negative ions moving towards the positive electrode, sorry, and the positive ions moving towards the negative electrode, and that is going to create a situation where we're going to have charges flowing around this circuit. Now, it says that we need to how does the flow of current, and again it says how does the flow of current, so we need to know what is current flow, right? So what is current flow? What is current flow, essentially?
The flow of electric charge.
Flow of electric charge, right? So current flow is just the movement of, I'm going to say simply, charge, right? Electric charge. So our current flow is just essentially the movement of charge. So inside the solution, as we said, we're going to have both positive ions and negative ions moving. Now, for the copper wire, we're only going to see that we're going to have the electrons moving, right? So let's just make a note on that. So let's say now in the cell, both positive ions, right? And if you want to show off, your chemistry knowledge, the positive ions, those are what? Cations, right? So the cations and the negative ions, both positive ions and negative ions, move, while for the copper wire, only negative, and these are not ions but electrons, move. Right, so inside the solution it's a movement of positive and negative ions, while inside the wire it is moved due to the movement of electrons. All right, next question now says that we're to name the material used for the positive terminal in a dry cell. So If we can remember the basic structure of the dry cell, we have our central rod like that, and we have surrounding it a particular electrolyte, and then enclose that we have our zinc. Right, and again, obviously, we're going to have other coating, but this is just the simple description of it, or the simple diagram of it. So for the positive terminal, we use carbon, right, for the positive terminal. Right, so the central piece would be your carbon, right, in the center, and then this, as I said, now would be your zinc, and then inside there, we'll have an electrolyte, that will be present inside this dry cell. So continuing, it says that name the material used for the negative of the dry cell, and for that we use the zinc for the negative terminal. So this is going to be zinc, right, like that. Now next it says that in the circuit in figure 1, if the current is steady at 0.1 amperes, calculate the charge that goes through the copper wire in 60 seconds. Alright, so for this, to find the charge, we can say that Q is equal to something. They gave us the current and they gave us the time, so we can relate the charge Q to the current I and the time T. Okay, so somebody calculate already? Okay, good work. Alright, so since we say that Q is equal to IT, and when we're working these questions, we always want to plug in the formulas. State the formulas and then we'll plug in the values. So I is 0.1 ampere and time is 60 seconds. So we multiply them and we indeed get 6 coulomb. So that's the charge with 6 coulomb, and we can claim those 3 marks. Alright, move again. It says now determine how charge goes through the simple cell in 60 seconds. Right? Oh, sorry, it says determine how much, Determine how much charge goes through the simple cell in 60 seconds. Alright, so let's see this now. So it says determine how much charge goes through the simple cell in 60 seconds. So again, we had our circuit, right? We had our circuit like that, and we inside the copper wire we have a current of in the circuit like that. Right, so in the copper wire we have a steady current of 0.1 amperes, right? And in 60 seconds we found that we have 6 coulomb of charge moving. So in this case now, they say we need to find out how much charge goes through the simple cell in 60 seconds. How could we work that question?
Maybe the second the subject.
Maybe the second the subject. Alright, well, let's kind of reason it out.
Is they can scroll up, so we are evaluating all one.
Yes.
Right? Because again, we just saw that in the wire, we have 6 coulomb of charge. Right? We have 6 coulomb of charge. Now, in this case, we say determine how much charge goes through the simple cell in 60 seconds. So, let's kind of reason this out. So, inside the copper wire, we're saying that, okay, we're going to have 6 coulomb of charge, which is due to the movement of electrons. Now, inside the cell, we said that we have both positive and negative ions moving, right? We have both positive and negative ions moving. So let's just consider something for a second. Let's say that we have 3 negative ions, right? Let's say like that moves towards this positive electrode, and we have 3 positive ions moving towards this one. Now, what we see now is that because there is an accumulation of positive charges on this side and an accumulation of negative charges on this side, and we connect that to an external circuit, what we're going to see now is that we can have charges now moving. So since we have an abundance of negative charge here, those negative charges can start to migrate. So let's say we have a single charge that moves around towards the negative terminal externally. So as a result of that, we can have a current flow due to the movement of that single charge. So how does that apply to what we have right here? Because again, it says determine how much charge goes through the simple cell in 60 seconds.
Sir, could I use the Q equal NE formula? I don't know.
Q equal NE.
Yeah.
I mean, yes, but I mean, the thing is, we don't know how many charge. Well, we're trying to find how many charge, right? So we're trying to find N, right? So let's see that. So if we say Q equals NE, right? Q is equal to NE. Now again, E would be equal to 1.6 times 10 to the minus 19 coulomb. But again, just from the fact that they say, okay, determine how much charge, right? Because they said determine how much charge, we could consider that they want us to use something related to what we would have obtained here, right? So in the copper wire, we would have found that, okay, we have 6 coulomb of charge. Now, in the cell, right, we should have that same amount of charge flowing. But again, due to the fact that, okay, we have both positive and negative charges moving, right? We have both negative and positive charges moving. But again, in terms of the quantity of charge, the quantity of charge would be the same as what would have flowed in the external circuit. So in this case now we can just simply say that, okay, the quantity of charge Q would just be equal to 6 coulomb. Okay?
That's it.
Right? So we're going to have 6 coulomb of charge. Alright, now
Sir,
next question now says, yes.
Sir, would I lose marks if me just said what?
No.
Oh, all right.
But again, you have to say 6 coulomb. If it says just 6, you have to say 6 coulomb.
All right, sir.
Alright, so next one now says identify the type of current, DC or AC, which generated the specific waveforms A, B, and C as shown. Alright, so for this one now, type of current?
Say DC.
DC, right? Easily. This one?
DC.
DC as well.
Alternating.
And then here?
AC.
Right? AC. Right, good. Right, so we have DC, DC, and AC. And this DC is what we got from the half wave rectification. This one would be from a battery, and this one would be from obviously an AC source. Alright, now it says determine the period and frequency for waveform C. So we have current against time. The period is the time for one cycle. Now one cycle would be this pattern like that, which would be 0.2 seconds. So we can say that the period T is 0.2 seconds. Now recalling that the period and the frequency are related by the formula, we'll say F is equal to 1 over T. Right, so I need to write the 1 first. 1 over T. So we say 1 divided by 0.2. And this is what?
0.5.
Sir, 5, sir.
Right, so 5 hertz. Right? So 5 hertz, 0.2 seconds. Right, so that's that. So that's 2011 completed. Now this is 2012. Alright, so we have this thing right here which involves a graph. Alright, let's see how we can do this. I think I want to plot this graph.
Sorry, I can scroll back up a little bit so we can take a screenshot.
Here is good?
Yes, sir.
Okay. All right. So let's see this question now. All right. So let's see what they say we need to do. We need to plot this graph, state the physical property, and so forth. All right. All right. Let me just do this question. All right. So I'm going to let me bring this over because I'm going to use the other screen so I can get the graph sheet. All right, let me just copy this. All right. What do I do again? Go here. And then go window here. All right. Where are we now? Right here. All right. So hopefully I can get the graph sheet in for this. So that's our table. Let me get the graph sheet. Give me a second. Where's this graph sheet? All right, it's actually there. All right, so so we have that in place. This goes here. All right. Okay. All right. So this is what we have. So let's give us this thing, and let's say plot a graph of current, sorry, of potential difference versus current. So since they say we need to plot potential difference versus current, we're going to have potential difference on our y-axis and current on the x-axis. So we can drop our axes. All right, I'd like to do that first. So let me just do this quickly. So this is our horizontal axis, so we can label it x. And then we have our vertical axis, like that. And we can refer to that as y. Let me just go all the way with this. So this one is y. And they say we need to have potential difference on the y. So I'm going to say PD. And that's measured in volts. And then we have current. That's I. That's measured in amperes. All right, so that's what we have. We have our origin, like that. And we have potential difference on the y that goes up to 45. So I can probably try a scale of 2 centimeters to 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45. That looks like it will work. So with 2, it's going to be 5. So that's 5, 10, 15, 20, 25, 30, 35, 40. Right, and then 45. So this is a reasonable scale because it allows us to plot all the points and it takes up a significant amount of the graph sheet. So that's the y-axis. Do the same thing on the x. Let's use this color. So the current goes up to 0.6. So I can probably use every 2 centimeters I go 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. That looks good. So 0.1. 2, 3, 4, 0.6, 0.7, and then 0.8, right? And again, we have to tell them, okay, what scale we use. So we say 2 centimeters equals 0.1. Let's take time with that. So 2 centimeters equals 0.1, and the unit is ampere. While for this one, we say 2 centimeters is equal to 5, and that's volts. All right, so we done the, I guess, hardest part. Now, next we need to plot the points. So let's use that color. So PD 1.5, current is 0.2, my bad, 0.02. So let's see how we can do that now. So we can find 1.5. All right, so when we're plotting the points, we need to know what is the value of each increment value on each axis. So we can determine that by simply taking the difference between any two consecutive points. So let's say 5 and 0, the difference of 5 and 0 is 5. So we say 5 and we divide by number of incremental lines. In this case, we're going to have 10 if we count them all up.
0.5.
So we get that. Right, so this is 0.5, good. So each line is 0.5 on the y-axis. We can do a similar thing on the x. So this is going to be 0.1.
0.01. 0.
Right, and we have 0.01, right? Good. So the first one we're looking for is 1.5 on the y, and I think 0.02 on the x. Let's confirm it. So since we're going up by 0.5 each time, we have 0, 0.5, 1, 1.5. So 1.5 is going to be the third line up right there. And then 0.02. So each line is 0.01. So if we can see this clearly, 0.01, then 0.02. So our first point, I'm going to just use an X to represent it. So again, might not be precise, but on the graph sheet, you know, you can plot it precise with your sharp, dark pencils. All right, next one, we have 4 to 0.05. That one is a little easier. So 0.05 is going to be here, and then 4 is going to be 2 lines before we reach the 5. Again, because I have to be lining this thing up. Hold on a bit. Hold on a second. This thing trying to fail me. Alright, bear with me a little bit. Just some technical problems. Okay. All right. So we said 4, I think 0.02 or something. No, 4 and 0.05. So 4. So again, this would be 2.5 right here. All right. So let me see if I can do this quickly. So 4 and 0.5. So if you can agree with me, it's going to be right there. Next one, we have 10 to 0.15. Or is that 1.5? Yeah, 10 to 0.15. So 10 to 0.15 is going to be in between, like so. Next one now is 18 to 0.24. So 18.2424 would be about right here. And 18, so this is 15, this is 17.5, so 18. Right, so I'm using reasonable estimates to help me out, but again, you can always use the smallest division and just count up accordingly to determine the plotted points or the points. So this is 30 and 0.4. So 30, 0.4. So that's right here. 30. So that's that. And the next one we have 45 to 0.6. So 0.6, 45, so that's all the way here. Right, so those are our data points. So now we can take our ruler and draw our line of best fit. So it's a line that will go through as many points as possible, and we aim to have an even distribution. All right, so let's see. So we have 1 point on this side, 1 on this side, and 1 on that side. All right, so let's see now. All right, so let's do this. So we have going through all these. We have 1 on this side, 1 on that side, so we can draw this as our best fit line. All right, so that's that for the graph. I mean, we put in our title. So PD versus current. Again, this is a lazy title, but you will obviously write in the title in more detail. But I just wanted to ensure that we do everything to secure the 8 marks. All right, are we okay with this?
Yes, sir.
All right, good. Now, next thing they say now we need to do is to calculate the gradient of the line obtained in A. And notice they say strictly, do not use any points that coincides with any from the table. So we can choose 2 points far apart and we can find the gradient. So let's use maybe this, no, let's just use yellow. So I'm going to select 2 points and I'm going to try to select points that I can read off quite easy. Let's try this one. Right, and then broken line across, straight like that. And then we'll choose another one. Say this one is ideal. Right, and then we'll do the same thing now for the x-axis, and I'm going to just demonstrate the gradient calculation quickly for our understanding. All right, so let's say this is our y2 value. That's going to be something like, since we said it's 0.5, so that's 40, 40.5, so this is about 41, and this is volts. This one is right in between the middle, so we're going to say 7.5 volts, and this is y1. X2 now is going to be, this is 0.55, so x2 is 0.55, and this is amperes. And then this one now is x1, and that's 0.1, that's ampere. So now we say that our gradient m, and we always have to write out our complete formula. Gradient m is equal to y2 take away y1 over x2 take away x1. x2 take away x1. So this now, y2 we say was 41 volts. That's 7.5 volts. And then now this is 0.55 ampere. And this is 0.1 ampere. So we say that minus that should give us something like
the white thing still there, right?
The layers.
okay, all right. Okay, all right. Hold on. Let me I have to like leave and then come back. All right. Let me try that. All right. I no. Maybe if I stop presenting and present again, maybe it will go. Yeah, is this better now?
Yes, sir.
Okay. All right, so this now we're gonna give us something like what? 43.5 or something. No, 33.5 or something. What is work with?
So you want the final answer or calculate it again?
Numerator and
Oh,
then
so
denominator.
33.54 plus
0.45 amperes. And then this now evaluate to be
74.44 approximately.
74.44.
okay, and this will be volts per ampere.
So wouldn't that just be ohms?
Oh, okay, yeah, we could say ohms. Yes. All right, but I just wanted to show our unit, right? So this would be 74.44, and 1 volt per ampere is the same thing as an ohm, so we can have it as that. Okay. All right, so
Sir,
that's that. Yes.
so the gradient gives the resistance.
Yeah, man. In this case, right? In this case, because of 4 units. So this is, as I said, would represent our resistance. All right, let me see if I can go back to the screen now for the questions while this thing giving me problems. All right. All right. Here, where do I go again? Right here. All right. Okay, so it says that for that part, and then next thing now. Next thing now it says state the physical property of the device with which the gradient is associated. So we can say what would be our physical property right here. What would be our physical property?
Resistor?
Resistance, right? So resistance. Let's just be straightforward, right? Resistance. So the physical property, right, of the device, with which the gradient is associated, will be our resistance. Now it says, using information from the graph, comment on the relationship between the potential difference and the current. So if I were to
So the potential difference is directly proportional to the current as long as the resistance is constant.
okay, right. But since it says we should use information from our graph, right? Because it says using information from the graph, as it rightfully said, in relation to Ohm's law, potential difference is directly proportional to the current, but they said they want us to use the graph. So since our graph, we had potential difference against current, and our graph looks like that, and it passed through the origin, we can say that the potential difference is directly proportional to the current, right? And sometimes they might ask, okay, why? Right? So we can say, you know, since a straight line through the origin
Sir,
was obtained, yes.
It's proportional because the resistance is constant, right?
Yes, it will be directly proportional because the resistance is constant, which was what was mentioned earlier. Right? But again, since it says, you know, using the graph, we can relate what we are stating to the graph. All right, let's see again. All right, so it says now draw a labeled circuit diagram to show how the student should have connected his or her apparatus to conduct the investigation. Now, this circuit, it's a very popular circuit that they love to ask. So if you're doing electricity, doing physics at least, for the electrical portion, if you don't know any circuit to draw any circuit, you must be able to draw this circuit, plus you must be able to draw a series circuit and a parallel circuit. I'm just starting with this box like that. No, I shouldn't do that because I can't erase part by part. I just remember. Alright, so I've got to draw this in stages. So I wanted to use colors and so on, but I'm going to try that as much as possible. So we're going to have our power source like that. Right, and then we're going to continue like so. And we always want, when we're drawing circuits, we are mindful of safety devices. So you always want to draw the circuit diagram and you show, okay, a switch like that. And then from the switch now we can consider, because we have to measure the current. So to measure the current we have our ammeter. Let's make that here. Right, and ammeter is always in series. Now we need something to vary the potential difference across the resistor. So for that we use our rheostat, which we can draw like this. So that's our rheostat. It says draw a label. Okay, so we're going to have to label that. Alright, so we go like that, and then we can have our device or the resistor. Let's place it right there. Let's make it maybe this color or this one. No, let's try this one. So this is our fixed resistor like so. Alright, so that's our circuit, and I say we need to label it up, so let's ensure that we do that. So we have our battery, we have our switch, we have our ammeter, and we have our rheostat.
So the voltmeter.
The voltmeter.
Okay, good question. I was going to ask, if we've complete everything, because we can measure the current right here, but we need to measure the voltage or the potential difference. We have the rheostat.
Why you need 5 2 resistor?
Why you need 5 2 resistor?
Because again, we need to vary the potential difference across our fixed resistor.
Oh, across. Oh,
Cross.
oh, alright.
Hold on. Give me a second, this thing. Give me a difficult time.
So that then mean the voltmeter will be connected right where the fixed resistor is.
Yes, it's going to be connected across here. So let me do that. Alright, so we're going to have something like this. Just bear with me. The writing pen kind of glitching out. It should be a circle, by the way. And inside the circle, we're going to have a V for the voltmeter. Right. Hold on a second. So as I was saying earlier, this circuit is a very fundamental circuit for electricity. Should be able to recognize it and should be able to draw it as well as label it, which is what we are trying to do right here. Alright, so give me a second, please. Right, just a second. Let me try to see if I can use a different connector. But in the meantime, any question, anything that we have been concerned with in terms of this section of the syllabus, or even any other questions that we would have looked at thus far? Anything in particular? Any particular question or topic that you would have wanted to see us work a question
The
on?
pressure in water.
The pressure in water. Pressure in water, okay. That's more like
Yeah,
mechanics. Anything related to electricity?
Sir, I have a question. So,
Yes,
are
please go.
we only gonna be doing what we're doing now for section D alone?
For
No,
today?
like I don't know.
For the
Yeah,
exam?
for the exam.
For I mean, what we would have covered so far, because if I were to go to the syllabus, I mean, we would have looked at electrical charges, somewhat. We didn't look at charging and charging by induction, different methods of charging. We didn't really look at electric field in terms of any questions thus far. We start to look at current electricity, because we spoke about the fact that in a metal it's due to electrons, right? And we also looked at the cell. So as I said, this essentially gives you a complete overview. I mean, we would have looked at applying this equation as well. So we see, okay, we would have hit some of our specific objectives in terms of what our syllabus expects us to know, right? I mean, we would have looked at this AC and DC. We look at voltage and current times graph and relate frequency and period. We start to look at this somewhat because we'd have looked at the power formula. So as I said, based on the questions that we would have looked at so far, we're seeing the different objectives that, the specific objectives that we would have been able to come across. So what we're doing with this session is to give everyone an opportunity to see how to apply the concepts that they would have learned, or also to introduce it to some of these concepts and see how they're actually applied to the different questions. So again, if you look through the syllabus, you're going to see everything that is expected. And that is why I would have chosen to do a series of questions so that we can be exposed to those different aspects that we can come across for the physics exam, or for this section at least. Okay?
Okay, sir.
Excuse me, sir. The PDF with this document, sir. Would you be able to release it?
Yes, man. I can definitely.
Okay, sir. Because we got my class got the link from our teacher, sir. So I'm not sure if you'll be able to send it to us, too.
Oh, okay, all right. Oh, yes, that's gonna be a challenge. All right, let me something now. All right. How can I do this now? Can anybody suggest a way that we can make it work? What's the easiest way we can make this work?
Sir, I mean,
Works, sir?
the same way we got the link would be the same way we get the document.
Okay. All right, so I guess I can just share it with because I would have shared it with some other teachers, and they would have shared it with you. So I can do that. Also, let's see this now. All right. All right. All right. We'll figure it out. We'll make it work. All right. Because I'm thinking how to make it that work, and I'm also thinking how to get this thing to work in front of me. But it's giving me a tough time. All right. Anyways, let's not cause that to delay our progress. All right. So let's see. All right. So again, we would have to label this our resistor, right, and our voltmeter accordingly, right? So forgive me with that in terms of the complete labeling.
All right, sir.
Okay.
All right, sir.
All right. All right. Let's see if this can pull us through. No. It worked for a moment and then just stop. All right. Anyways. All right.
Oh, sir.
Let's see
So
what we
we're gonna
can do in the
try.
meantime.
We're
All
gonna
right.
try the box one.
Yes.
So like we make and type it.
try the box one, like we make and type it.
Just press it
Oh, that
up on
way
the
now.
top left. The T one, not the A.
This one?
The T on, not
Just
the A.
press it and
Okay.
type.
All right. Cool.
Just press it and type.
Yeah. All right. I never know about that. All right. So, so I can click and drag after I click. All right. So this would be our resistor. Right, and this would be our voltmeter. All right, good, that works. All right, so that's our circuit diagram. Now it says, with reference to 1E, describe the procedure used to conduct the investigation. All right, so we want to describe the procedure in terms of how this can be done. So let me see if I can do this in bullet points. So the first thing we do is to set up circuit as shown. All right, that's easy. All right, then 2, we're going to after we set up the circuit, we're going to record the current and voltage, right, from the ammeter and voltmeter respectively. All right, so we measure the current from the ammeter and the voltmeter respectively. Then 3, we're going to slide. Again, I'm kind of jumping through some things. I mean, you set up the circuit, you're going to close the switch, and then you're going to take your reading, right? Then you're going to open the circuit and slide the rheostat to change the current flowing in the circuit. So quit, right, like that. Then 4, you're going to close the switch and record the current I and voltage V, right? And then you could say step 6, repeat for several readings. All right, so we could do that. All right, so that's that, right? That works for us.
Sorry, I mean slide. Slide the rheostat.
Okay, so yeah, so the rheostat, it has a little
It's
so
like a turning
rheostat.
thing.
It's like a turning thing. Oh yeah.
All right, let me kind of skip it. So the rheostat, you have a little section like that, which is cylindrical, and you're going to have a little movable thing at the top that you can slide down or slide up to change the resistance. Right? So that's what we're going to move. Right? Now, it says now 3 devices with resistance 8, 12, and 15 are connected in a circuit. Find the combined resistance when these devices are connected in parallel. Alright, to type this might take a while. Hopefully this works. Alright, anyways, let's try a thing. So to find the total resistance, we have to say 1 over RT must be equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? So we take 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So then now we get, if I can change the color here, so we get 1 over RT, when I say we need to find the combined resistance, so that's RT is going to equal to 1 over 8 plus 1 over 12 plus 1 over 15. All right. So now, essentially what we're going to see is that we're going to have our fractions. All right, we're going to have our fractions, 1 over 8, 1 over 12, 1 over 15. And for this, we can find an LCM, right? 8, 12, and 15. What will be the LCM of that?
30.
What will be the LCM of 8, 12, and 15?
30. Sir, 1.
30.
120. Sir,
120.
120. 120.
120. All right, so this would
Sir,
be
30.
120. If I can do this,
Sir, 30.
it wouldn't be able to go into 30. All right. So we're going to get 8 into that. 8 into 12 goes what? How many times?
Sir, 1 time. Sir, 8 into 12 is 1 time. Oh, 8
8 into 120.
Oh,
Not
50.
120.
Oh, 8 into 120. Oh, 50.
All right, 15. So, all right, let's try that. So that's going to be 15 plus the next one was what? 12 into that goes 10. So we're going to say 10, right? Plus 15 into 120, that's what? 8 times, right? So what we get then now is we're going to get a situation where we're going to see that let's change this color. So we're going to see that 1 over RT is going to equal to 15 plus 10 plus 8. That's what now? 25, 33. So 33. Sorry, that's the wrong button. So we're going to get 33 over, that's what now? Over 120.
Yes,
All
sir.
right, that's good.
Yes, sir.
So now, to find RT now, we're just going
Reciprocate.
to invert.
Reciprocate.
Right, yes, that's the word. Reciprocate. So we're going to get RT now. RT being equal to 120 over 33. So we'll just evaluate that now. And we get RT
0.7.
being equal to
2.7
how
ohms.
much?
3.7 ohms.
3.7, okay?
No, it
So
can't be
3.7, let's
3.7.
write it out.
3.64.
3.64.
Okay, so round off to
Round it
much?
off by
So
2 dp.
3.6.
3.6.
2 dp.
Right?
3.6.
Right, so 3.6 ohm. Right? So RT would be 3.6 ohm for that. All right, let's go again. All right. So it says describe an experiment that can be used to determine the resistance of a metallic conductor. So this question would basically be this right here. All right, so we can set up our circuit like that and we can do this. So this would apply this would apply to what we just discussed earlier. All right, let's try this. All right, give me a second. All right, let's try a thing with this. All right, so it says describe, as I said, we can apply the information up top here to score those marks. Now this one now says figure 2 shows a 12-volt battery of negligible internal resistance connected to an arrangement of resistors. It says that given that resistors R1 to R4 each have a resistance of 3 ohm, calculate the total resistance of the circuit. All right, so let me see if I can do a thing. So I'm going to isolate this portion of the circuit. And for this portion of the circuit, we have these two resistors, R2 and R3. Right, R2 and R3, how are they connected in this?
Parallel.
Parallel. Parallel.
right? They're connected in parallel. So we can find the total resistance for these two resistors in parallel. And since we have two resistors in
Should be
parallel,
1.5.
we can take our,
Oh,
huh?
sorry. I was saying that it was 1.5, but yeah, it's approximately.
Yes, yes, 1.5, right? And we can show the calculation for that by taking the product over sum. So we can say product over the sum, right? And we do this because we have two resistors. So therefore RT now is going to equal to the product. Both of them are 3, so we're going to have 3 times 3, which is 9, divided by 3 plus 3, 3 plus 3, which is going to give us 6. So RT then now, RT then now is going to equal to, so we get 3 times 3 is 9, divided by 6, and 9 divided by 6 should give you, as I said, 1.5, and this would be ohm. Right? And again, this would be 1.5 because, I mean, when we have two identical resistors in parallel, the total resistance is always half of their individual resistance. Alright, so that's just for the parallel part, 1.5. But we also have R1 and R3, sorry, R1 and R4. Now what we're going to see now is that our circuit, we can now consider this as, instead of having two resistors of 3 ohm and 3 ohm, we can just treat this as one resistor of 1.5 ohm. Again, just bear with me with this, please. Alright, are we making sense so far?
Yes, sir.
So now we have these three resistors in series. Now to find the resistance, total resistance in series is just a matter of just adding. So we're going to add 3 plus 1.5 plus another 3. So that's going to give us 7.5, right?
Yes, sir. Repeat out this.
So we add 3 plus the 3 plus the 1.5 to give us 7.5. Right. Now, next question says we need to find the current drawn from the battery. So to find the current, we can work it over here. So we're trying to find the current. So we can say that current I is equal to V over R from Ohm's law. So if that's the case, then we can say that I must be equal to
1.6 ampere. Yes, sir.
1.6. That's answer. All right, so let's see now. So V, let's say, was 12. All right, 12 volts. All right, and we divide that by R, which we said was 7.5. And that's ohm, OHM. Right, and we say that equal, how much you say?
Yeah, 1.6.
1.6. Exactly 1.6.
Yes, sir.
And that will be ampere. So that's the current, 1.6 ampere. Now, it says now we need to find the voltage across R2. All right, so voltage across R2. All right, so for this situation now, we have to take into consideration our circuit. All right, so similarly, well, several ways we can actually look at this. All right, several ways we can look at this. All right, so we can look at it from the perspective of, okay, we have a series parallel circuit. So we have resistors connected in series and we also have resistors connected in parallel. Now what we're going to see now is that in a series circuit, the current is always the same throughout. So if R1 and R4 are in series, then the same current will flow through them. But R2 and R3, when they're parallel, the current is going to split between them. And the voltage is constant, right? So in parallel, the current splits, voltage is constant. While for the series, the current is the same or constant, and the voltage is shared. So now, if the current is the same now, let's say what we need to find, we just find the total current drawn from the battery. Say it was 1.6 amperes. So we're going to have 1.6 ampere flowing It's going to go through R1. When it reaches right here, it's going to split. So some going to go through R2, some going to go through R3, then it's going to join back together, and then we're going to have 1.6 flowing through R4. Now, in this case now, because both resistors have the same value, what we're going to see now is that the current is going to share between them evenly. So if it's 1.6 that comes right here, you're going to have half going through this one, and you're going to have half going through that one. Make sense?
Yes, sir.
Yes, sir. Right, so we have half going through this and half going through that. So now, if that occurs now, we want to find the voltage across this one. So we can remember somewhere that Ohm's law tell us that
Equal I
V
times R.
is equal to, right, good. So V is equal to IR, like that. And in this case now, that's going to be equal. I can line them up perfect. It's going to be I is, we say half of it, so it's going to be 0.8 ampere times R, which is, all of them is 3. So this is 3 ohm, OHM. And 3/8 is 24, so this is what, 2.4? 2.4, right?
Yes, sir.
And that's volts, right? So that's how we can apply this, right? Any question about that?
Sure.
Any question for that?
Also, when you say
Yes.
1.5 times 1.6, you get 2.4.
1.5 times 1.6. Okay. So 1.5 from the total resistance. And all right, so 1.5 would represent the total resistance right here, and 1.6 would represent the current flowing through. Right, because essentially you're also gonna get 2.4, because if you think about it this way, these two resistors, right, they combine to form an effective resistance of 1.5, and the current flowing through them is, our current flowing through it, if we consider these two as one, is going to be 1.6 amperes. Now we were trying to find the voltage, and remember we said earlier that in a parallel circuit, the voltage is what? Constant, right? So the same voltage across R2 is going to be the same voltage across R3, right? So if you treat this as one resistor, you're also going to get 2.4. So that's another way that you could have looked at it. But in a case, where, let's say the resistors were not identical, you might have to be a little careful with that.
Yes, sir.
Okay? Yes, sir. All right, well, that's good. All right. 1 second, please. All right, so let's see if we can continue. All right, hold on a second, please. All right, let's continue because this thing still not connecting. All right, okay. All right, so just checking in. Are we good
Yes,
so
sir.
far?
Yes, sir.
Okay. All right. Cool. Good work. All right. So let's continue with this if I can. All right. So we just did that question up top. Now it says explain what is meant by the term electrical resistance. So electrical resistance. This is the ability of a device to resist the flow of, we could say, electrical charge. All right. So resistance is just the ability of a device to resist the flow of electrical charge. All right, and that's one mark.
So question.
Now it says complete table.
So they penalize you
Yes.
for using the same word back in the thing.
No, they wouldn't, because I mean, all right, well, it depends on, because if you say okay, all right, what would you say? Let me hear what would you say first of all.
So just say,
First, I was kind of actually thinking about using resist, use the word resist also, but also bring in back the whole using same word in explanation. But let me see if I can make another one. Electrical resistance is the ability of a circuit or no of a electronic device to slow
to
or
oppose.
to slow down the current in that circuit.
Yes, and to say slow down the current, I mean, I would prefer you say
So
reduce
also
Oh yeah,
opposite.
reduce, yeah,
the
reduce
So
circuit.
also opposite.
yeah. Yes, one more
It also
question.
is the word opposition.
Right, oppose, right. So instead of resist, we could use oppose, right? Yes, right. Or we could say prevent, or because depending on the resistance, it can prevent the flow of charge. All right. Now it says this. We have this thing to complete. It says we need to state how it is connected in the circuit, whether it's series or parallel. So let's do that. So the ammeter. How do we connect an ammeter in the
In
circuit?
series.
In series. All right, so this would be series, if I can spell series, series, series. What about its resistance?
Low resistance.
Right, and why? Oh, that's the reason why. So I was just gonna ask why. So this is low, and we want the resistance to be low to ensure that the ammeter does not affect the circuit. Right? So we want to have a low resistance since we're connecting it directly into the circuit. So we want the resistance to be low such that it doesn't affect the circuit. Now for the voltmeter now, how do we connect the voltmeter in the
Parallel.
circuit?
Parallel.
Right, so this one would be parallel, and
Is high.
distance, right, high. And why want
They
it to be
do
high?
affect the circuit because the current will take the easier route.
Exactly, right? And really we could say to ensure that no current flows through the voltmeter. So as I rightfully say, the current always take the path of least resistance. So if you have a very high resistance, so if we go back up to our circuit right here where we drew, so if we have a high resistance voltmeter right here, when the current is flowing around, once the current reaches right here, it's not going to flow through the voltmeter, it's going to continue here, and we can measure the potential, right, across when we place it in parallel. While when we place the ammeter in series, we can measure the current going through. All right, that's that. All right, so this question now says we need to calculate the reading on each of the meters shown in the circuit in figure 2 when the switch is closed. Absolutely. Let me do that.
Stop.
Yes, that's
Yes,
good.
sir.
Okay.
So you can continue.
Okay. All right. Hold on a second. All right. So for persons who wish to join the marathon, the complete marathon, which will be later down, you can register using the link that I would have just shared in the messages. All right. But as we continue, all right. So it says we need to calculate the reading on each of the meters shown in that. So okay. So we have this one right here. All right. So this says reading on ammeter 1. All right. So to find the reading on ammeter 1, we have to do a little bit of analysis of our circuit. So the reading on meter 1 would indicate the total current flowing in the circuit. So we need to know what is the total current. So we can say that the total current, if we call that IT, IT will be equal to, so since I is equal to V over R, it's going to be equal to V divided by R, but the total resistance, RT. So the total current IT, which is going to be on ammeter 1, is going to be equal to the voltage of the source divided by the total resistance. So what it means, therefore, is we need to find the total resistance. So again, we can do a little bit of isolation. So we see that we have these two resistors right here. We have a single path for the current to flow. So since we have a single path for current to flow, then these resistors are connected in single
Series.
path for the current to flow. They are connected in series, right? So we can say then, let's say we call this one REQ for the equivalent resistance is going to equal to R1 plus R2, right? Which becomes R1 is 2, so we're going to say 2. And I'm not going to put the unit right here to save time. 2 plus 4. Sorry, what did I do? 2 plus 4 is simply 6. So this is 6 ohm. Right, so we have these two having an equivalent resistance of 6 ohm. Now these two resistors, so again, here we have two pathways. So a pathway here and we have one right here. So the current has two pathways, so therefore this resistor is connected in parallel to this one over here. So then we can now show on this side that RT, since we have two resistors in parallel, is going to be the product over sum. So product over the sum. So that's going to be equal to the product of 6 times 2. And we have to now divide that now by 6 plus 2. So we have 6 times 2 is 12. 12 divided by 8. That's what? 1.5 or so.
5. 1.5.
1.5. Okay, cool. So 1.5, I'm going to say now that's going to be ohm. Alright, so now we know the total resistance. We can now say that the total current, IT, must be equal to, we say it was V over R, so that's going to be 12 divided by 1.5. And that's going to give us what? What's 12 divided by 1.5?
8, sir.
8, so this is going to be 8 amperes. All right, so that's the reading on the first ammeter, 8 amperes. Now it says reading on ammeter 2, which is A2. All right, so let's see this now. So we have this being 6 ohm and this being this is what, 2 ohm. Now we can say, okay, since we know that, okay, this is parallel, the current is going to split. And the current, as we said a couple seconds ago, always take the path of least resistance. So if we have 8 ohms flowing, and this is 2 ohms and this is 6 ohms, we're going to expect more current to flow through this one right here, right? We're going to expect more current to flow through here. Now, we can take into consideration, okay, that, okay, this is 2 and this is 6. So this resistance, or the resistance on this side, is 3 times greater than this. So what we're going to see now is that the current flowing through here is going to be 3 times greater than this one. Now, as I said, that's what we expect, right? And we can show it using the calculations. But also, we can take into consideration that we have a parallel circuit. So we have this resistor connected parallel to a 12-volt source. So if it is connected parallel to a 12-volt source, then the voltage across it is going to be 12. So then, with that being the case, now we can say that I is going to equal to V, like that, divided by R. So we're going to say now V is 12, so that's equal to 12. And then R now is 2, so we say that's 2 ohm. And then that now is going to be equal to 12 divided by 2 is obviously 6, so we can say 6 amperes. So the current flowing here would be 6 amperes. Right? So the current is going to split such that 6 amperes flow here, and then the remaining 2 is going to flow through here. Now, okay, so that's that for the question. All right, so are we good with that?
Yes, sir.
Yes.
Okay. All right, so that's that. Okay, good. So again, remember, you guys can register for the marathon. We're going to be going through the entire syllabus, all sections, during the marathon. All right, now, here now, this question says, how does the electric current in a metal differ from that in an electrolyte? And we're going to compare each with conventional current. Now, what's conventional current?
Current that flows from positive to negative.
Right, so current that flows from positive to negative. So let me just make a note. So conventional current let's see if I can spell conventional current. Right, this now is simply
Sir, conventional current is just a phenomenon, right? Not a phenomenon.
yes, it's a phenomenon.
Yeah.
Yes, it's not real. Movement of positive charge. Positive. Sorry. Positive charge. So it was just an idea that that they would have come up with, but it tends to persist because of how closely tied it is to certain concepts, especially when we start looking at things like electromagnetism. All right, so okay, so it says that how it differ. Okay, electrolyte. All right, so I mean this was simply related to what we would have covered some time ago in terms of the cell thing here, right? Related to that in terms of both positive and negative ions move. All right, so let me go back to this now. It says compare each with conventional current. Okay, all right, so we want to compare the movement of charge in metal. So in a metal, we know that that is due to the movement of negative electrons, right? So in a metal, it is due to the movement of negative charge, while for conventional current, that consists of the movement of the positive charge only. Okay?
Yes, sir.
Right? And for the electrolyte, that's both positive and negative charges moving, right? While for the conventional current, that's just the positive charge. So since it says, okay, we need to state this and we need to compare it, so we have to make mention of what conventional current is, right? And then we have to now talk about the movement of charge in a metal as well as the electrolyte. All right, so hopefully we're okay with that. All right, state which of these two media, metal and electrolyte, has similar current flow to that in a semiconductor. All right, so in this case now, for a semiconductor, right, in a semiconductor, we also have positive and negative charges moving. So let's see what the question says. So state which of these two media, okay. So an electrolyte consists of the movement of both positive, so let's say plus VE, and negative charge carriers similar to that of a semiconductor, right? Similar to that of our semiconductor. And it's a give reason, so we can say that in a semiconductor, there exists the movement of negative electrons and positive holes, holes, I'm going to say across the p-n junction. Right, I might ask, okay, what exactly we're talking about, p-n junction, right? That's just basically, when we join a positive type, a p-type material, p-type semiconductor and n-type semiconductor. Now, in the electrolyte, we also have the positive ions and the negative ions moving, while for the p-n junction, we have the positive holes and the negative electrons moving across the p-n junction. So hopefully this is okay for us. All right. So that's that. Now, next question now says that the makers of a popular cell phone have upgraded its battery capacity from 4320 coulomb to 9000 coulomb. If the standard charger can deliver a current of 0.6 ampere, how much time will it take for the new battery? To charge how much time will it take? How much more time will it take to charge the new battery than the old battery? So, and just as I was stumbling over the reading a while ago, when we're attempting the questions in the exam, don't be afraid to read the question 2 times, 3 times, just to get clearly what the question is really asking, because that is the only way you're going to be able to answer the question correctly when you fully understand what is being asked. All right, so it says how much more time will be needed. So we can say Q, first of all, is equal to I times T. So Q is equal to I times T. So if Q is equal to I times T, then T must be equal to Q over I, right? That's true, right? T must equal to Q over I. True? So let's find the time it takes to charge the old battery, which has a capacity of that. So we're going to say T is equal to Q, so that's 4320 coulomb, and we divide that by the current, and let's say it was 0.6. So we get T would be equal to what?
7,200.
200, and this would be in seconds, right? So that's for the old battery. Now, if we do the same thing now for the new battery, we're going to have T is equal to Q over I, as what we just proved a while ago. So that's equal to Q, which is 9,000. And we'll divide that now by T, which is 0.6. Sorry, I should say 0.6. So that's what now?
15,000.
15,000.
15,000.
15,000.
15,000, okay. Alright, so this is equal to 1500, like that, 15,000, and this would be seconds. Alright, now it says how much more time will it take. So since the old one took this amount of time, then the time difference, so let's say T, right, would be equal to, we want to say delta T. T is going to equal to that number minus this number, which is 7200. 200. I'm not pressing all over the place. It's going to equal now to what?
7,800.
7,800, and this is too much zero, but that must be seconds. So that's that. It says now, in order to maintain a competitive edge, the cell phone maker needs to keep the same charging time for the new model. Same charging time for the new model, the same as the old model. Okay. What must the current rating on the new charger be to accomplish that? All right. So the first one took 7,200 seconds to charge. When the charge capacity was 4320. Now we have 9,000. I want to keep that same time the same. So we need to know the current. So we can say that the current I will be equal to, since Q is equal to IT, I must be equal to Q over T. So we say that the charge is going to be the same, 9,000. And then we have to divide that now by the time, which is say must be 7,200. So that's 7200. And this one now would equal to, what is equal to now?
1.25.
1.25.
Okay, so 1.25, sorry, 1.25, and this would be amperes. All right, so 1.25 amperes. All right, so that's that. All right, so here we have another graph question. All right, we could plot this graph, but because I'm having some difficulties with this thing. All right, so we're going to skip part A and B, and we're going to look at, but anyways, essentially, when you plot our graph, if I can sketch it, your graph is going to look something like this, right? Graph should look something like that, because what we see now is that as time increases, the induced EMF is actually fluctuating. So it's increasing up to some maximum value, then it's decreasing to 0, then it goes negative, right? And then where am I? Then it goes to a maximum value, negative, and then it starts to decrease. So we should get a thing like this, right? So that's that. Next question now says, okay, we can do that. We can't do that because we don't have the graph. But this question now says that Kevin who is a physics student, conducted an experiment to determine the effects of electromagnetic induction. He used the following apparatus: a coil made of fine wires, a sensitive galvanometer, some connecting wires, and a bar magnet. Now, it says that the magnet is pushed into the coil with the north pole entering first. And it says we're to draw on figure 1 the direction of the induced current and the direction of the arrow and the galvanometer as a result of this motion. Alright, so in this case, we have to take into consideration electromagnetic induction, right? Which basically says that once we have a change in magnetic field, we're always going to get an induced EMF. So let me just make a note on that. So electromagnetic induction. Right, so a change in magnetic field will always, let's say, will induce an EMF across a conductor in that field. Right? So electromagnetic induction basically says that whenever we have a change in magnetic field, it will always induce an EMF across a conductor. And let me just make a note that this change in magnetic field could be due to relative motion of the conductor with respect to the field, or vice versa, right? Or vice versa. All right, so if we have the coil moving, if we have the conductor moving or the magnetic field moving, then we're going to have a change in magnetic field, right? Or if we are basically increasing and decreasing the magnetic field, we're going to have an induced EMF. EMF, right? Electromotive force, which is essentially a voltage. All right, so that's that. I'm not sure if there was somebody who wanted to ask a question or something. All right. All right.
Sir,
Next question.
how would I tell the direction of the voltage if depending on the way on the magnet?
All right, so that's what we're going to discuss now. All right, so in this case now it says that the magnet is pushed into the coil with the north pole entering first. All right, so once we start pushing in the bar magnet with the north pole here into the coil, what we're going to see now is that because we're moving the bar magnet in, we're going to cause an induced EMF. Now that induced EMF is going to cause a current to flow. So we're going to have a current flowing through this coil. Now once we have a current flowing through a conductor, there is going to be a magnetic field associated with it. Now for a coil, the magnetic field behaves as if it's a bar magnet. So what we see now is that we're going to have one end of this coil being a north pole and the other end is going to be a south pole. Now, there's a very important principle known as Lenz's law, which says that, okay, when you try to create or when you try to induce a current, whatever you do to induce that current, the induced current is going to try to oppose that. Okay? So Lenz's law says that, okay, whatever you do to induce the current that is induced is going to oppose what you're doing. So, we can look at this now. Are you able to follow what I'm
Kinda
saying?
say. Really? Kinda say.
Right. So again, whatever you do, right, the current that is induced is going to oppose what you're doing. So it's like you're doing something to produce the current, but the current is going to try to prevent you from
Also, I like
producing
the
the
thing
current.
the law, one of Newton
Also,
law
I
them.
like the thing the law, one of Newton law them.
If action
Yes, I
equal
know.
opposite reaction,
Yes.
sort of. I mean, it is connected to that somewhat, but is more so connected to the concept of energy can neither be created nor destroyed. So anyways, if we are trying to put a north pole in, right, the current is going to flow to try to oppose that. So if we have a north pole right here, the only way we can oppose a north pole going in is if we put a north pole right there. That makes sense?
Yes, sir.
Right, so we're going to put a north pole right here, and then this side is going to be a south pole. Now, once we are at the north pole, right, I mean, I'm trying to find a simple way for us to really appreciate this. Once we have the north pole, so imagine that you take the solenoid and you're looking at it straight down. So you're looking down this end. Or in other words, you're basically like you're looking through the solenoid. So when you look through the solenoid, you're going to see something looking like this. Now, once we're at a north pole, the current will always flow anti-clockwise. So the current will always flow anti-clockwise at the north pole. And we can do that, or we can actually show that by using the right-hand grip rule, right? But in this case now we're going to modify it for a solenoid. So again, if we can just appreciate this for now, that the current is going to flow anti-clockwise. Can we appreciate that? If no, let me
Sir,
know.
but I don't see how if the North Pole is entering the coil at first. No, sir.
You don't see?
I
You don't
don't
see
see
what? I
how
didn't hear what you said.
because it says the North Pole enters the coil at first.
Right, so what I'm saying is that because the north pole is entering, we're going to get an induced EMF, which is going to cause an induced current. And that current is going to try to oppose the north pole going in. So the only way we can oppose the north pole going in is if we have a north pole right here.
Yes, sir.
You get that part? Now, once we're at a solenoid and we're at the north pole, the current always flow anti-clockwise at the north pole.
Sir, a
Also,
solenoid
use the right
is
hand grip road.
Yes, we use the right hand grip.
some type of temporary magnet.
Yes, once a current flows through it, it's going to
Okay, sir.
behave as a temporary magnet. Right? So we get the north pole and the current is going to flow anti-clockwise. So we're going to have the current going in this direction. If I can draw it. Where's the pen? So we're going to have current going this direction. So the galvanometer always point in the direction of the current. So it's going to go anti-clockwise. So it's going to be anti-clockwise, sorry, at the north pole. So it's going to flow down here. And then it's going to continue in that direction. All right, let me know if we're clear with that.
Yes, sir.
Right, so that's the direction right there. So it says do that, draw on diagram the direction of this current. Okay, so the current therefore now is going to be going down like that, and it's going to be going up like so. Right, so we get that taking place. All right, explain why an induced current is produced. Right, so it's really basically due to this. Right, so let me see if I can put this into wording. All right, an induced current is produced since the movement of the bar magnet into the coil causes a change in the magnetic flux, right, or field linked to the coil, right? So due to the change in magnetic flux or the change in magnetic field that is linked to the coil, we get an induced current, right? And that induced current is because we're going to get an induced EMF, which causes the current to flow, right? Now here it says why we use a sensitive galvanometer. This is due to the current being very small, and a sensitive galvanometer ensures the current can be recorded, right? So any slight current that flows, the galvanometer will detect that. All right, now the bar magnet is pulled out of the coil. On figure 2, which is this one right here, show on figure 2 the direction of the induced current. So in this case now, what we see now is we are moving the North Pole away. So again, by moving the North Pole away, we're going to cause a change in magnetic field. Now that change in magnetic field, was that a question? Right? We're going to get a change in magnetic field, and that change in magnetic field is going to cause an induced EMF, which is going to cause an induced current. And again, as I said, the induced current. No, that's Faraday's law. No, what Lenz's law says is that once the induced current flows, it always opposes the change. So now we're going to apply the Lenz's law now. So we're moving the North Pole away. So how can we oppose the North Pole going away?
Also, introduce a south pole.
Right, so this is going to be a South Pole, right? And then here now would be a North Pole. Now, similar to what we said in terms of the North Pole, the current always flow anti-clockwise. For the South Pole, the current is going to flow clockwise. So what we're going to see now is that the current is going to be flowing in a clockwise direction. So the current is going to be going upward. So the current is going to be going upward here, like that. And it's going to be going down here. Right, so the galvanometer will point in this direction. Right, if persons have questions, they can ask.
For questions like these, I just need to know like the rules and concepts, right?
Yes.
Sir, how do you know which direction the arrow goes?
All right, there's a wind blowing in your background.
Sir, hear me
I don't
now?
hear your question.
How do you know whether the arrow goes up or down?
All right, so again, what I'm considering is the concept of there's a rule which says that if you take a solenoid and you look through it, whenever you have the current going, whenever you have a south pole, the current always flow clockwise, and whenever you have a north pole, the current always flow anti-clockwise. Now we could have also used what we refer to as the right-hand grip rule, but I was kind of stepping away from that because it might require some demonstration, but let me just discuss what it is now. So the right-hand grip rule says that, okay, when you have a solenoid, if we would have identified the south pole and the north pole, we're going to place our right hand over the solenoid. Right? We're going to place our right hand over the solenoid such that the thumb, so imagine that you're placing your right hand over the solenoid with your thumb sticking out, because we're going to use the right hand grip rule, but we're going to modify it for a solenoid. So when you do that now, so if you can imagine with me, you place your right hand over the solenoid, right? But your thumb must point towards the north. So you're going to have to align your hand so that your thumb is pointing to the right, because the north pole is to the right. You with me with that? Now, once we do that now, we're going to see that our other four fingers are going to curl in a particular direction. So if you open your hand and then you curl it down, you're going to see that your fingers are curling down in the front, right?
Yes,
So they curl downward in the front. So what it means then is that at the front of the solenoid, the current is going to be flowing downward, right? So the current is going to be flowing downward. So the only way the current can flow downward at the front is if, as we trace it back, we see the current goes up on this arm, then down, and then around and around until it eventually.
so I understand it now.
Right, okay. Right, so that's what we see for that. Now it says state 3 changes or adjustments that Kevin could make in this experiment to increase the induced EMF. So we can increase the induced EMF by one, using a stronger magnet. Two, we could move the magnet faster, so we could increase the speed of the magnet in terms of its movement. 3, we could use thicker wires, THICK, thicker wires. And when we use thicker wires, that's going to reduce the resistance. So it's going to basically cause the amount of current to be increased. So use thicker wires, or we could increase the number of turns. So increase number of turns. Right. So these are some things that we can do to increase the what's the limit? Let's almost increase again. Increase what? The induced EMF. Alright. Alright, are we following that so far?
Yes, sir.
Yes, sir.
Now it says describe what will happen if the magnet remains stationary in the coil. What do you think will happen if the magnet remains stationary in the coil?
So check it out.
Huh?
No current will induce. No current will induce.
Right? Okay, so no current induced. And the reason for that alright, so we're gonna get no induced current, because essentially since the bar magnet is not moving, there's no change in magnetic field. So once the magnetic field is not changing, then no current will be induced. So we're gonna get no induced current.
So it's like a motor.
See this now? Alright, so it says no.
It's
Huh?
something like a motor.
A motor, well, a generator, because the motor takes electrical energy and gives you mechanical energy, right? So it will be more of a generator. All right, we'll continue with this one. All right, so it says now figure 3 shows a simple layout of an AC generator. A coil PQRS is connected to other components of the circuit which allow the coil to rotate in the direction indicated by the arrow. So in this case now what we have is, so this is also on the principle of, yes.
Okay.
Here?
Yes, sir.
Yes, sir. Okay.
Sir, the guidance something where they show like a document from the guy that the movie check the CSEC. You can study in the classroom.
Yes.
You can study in the classroom?
Yes, sir.
That's
Studying a
the
level R
syllabus.
classroom at Jamaica.
Yes, sir. Study in a level R classroom at Jamaica.
Yes, I know Jamaica.
Okay,
All
sir.
right. Yes, I'll send it for you.
Okay, sir.
Yes. All right. So yes. So here now, as I said, now we have this situation where we're going to have this coil rotating, and we're going to get an induced current, right? For our generator. So it says draw and figure 3 the direction of the induced current if the coil rotates in a clockwise direction. All right. So let's see this now. All right. So in this case now we have to consider Fleming's right-hand rule. So we're going to consider Fleming's right-hand rule. So we take our right hand, and just like with the left hand, where we have our 3 fingers aligned at right angles, we're going to do the same thing. But in this case, we're going to use the right hand. Now, once we do that now, the index finger or your first finger indicates the field. So the field is going to the right. So your index finger in your right hand is going to point to the right. And this side of the coil is going to move upward. So again, if you can bear with me, sorry that I don't have the ability to draw. But again, we take our right hand. So just work with me. So take your right hand. You want to have your thumb up in the, no, sorry, your index finger pointing up. You want your index finger point, sorry, what am I saying? You want your thumb to point up, right? Your thumb points up. You want your index finger to point out, and your middle finger pointing in that direction. So if you can get them like that, that's what we're looking for. Now in this case now, we have the index finger should be pointing from north to south because that's the field, right? And if it's moving clockwise as we see right here, side PS is going to move upward. So with side PS moving upward, so the thumb points up, and we see that our middle finger points into the page.
So my middle finger pointed down.
Down. Alright, so again,
Yes, sir.
right hand you're using. Alright, so take your right hand again. So point your index finger to the right. Right? And your thumb up. So when you point your index finger to the right and your thumb up, where the middle finger points.
Now going forward.
Right, so you're going forward. So it's going into the page. So we're going to have a current flowing into the page on side PS. Now if the current flows in on PS, the current automatically must flow out on RQ. So it says we need to show the direction, so we can just put a little arrow like that. Right, and a little arrow like so. Right. Now it says that if the period of rotation of the coil is that, calculate its frequency. So we can do that simply. So we can say F is equal to 1 over T. So we say 1 divided by 0.02. Oh. Mommy, that over. Alright, so we say 1 divided by that value, and this works out to be what? What would this be?
50.
50, right? So that's 50 hertz. Alright, now it says that if the speed and direction of rotation of the coil are constant, sketch a graph of voltage against time to show the output of the generator for one complete cycle if it starts from its current position. So let me just sketch this quickly. So we're gonna get an AC signal, which looks, this says one complete cycle. So we're gonna get something like that. Right. So that's what we get. All right, and that's our question. All right. I wanted us to all right. 1 second. All right. Okay. So we're going to close off this session here. So hopefully, from what we would have discussed, you guys feel a little more comfortable when it comes down to section D of the syllabus. Again, for persons who yes. All right. Good. So let me do that right now. All right. How do I write this again? All right. So again, as I said, hopefully from our discussion, you guys feel a little more comfortable with regards to section D of the syllabus. Again, for persons who wish to be a part of the marathon, yes, I could provide, well, I'm going to provide a link to the solution paper that we just worked through. Also, as I said, for persons who have not yet registered for the marathon, I would have just posted the link, so you can ensure that you register. It's going to be a full day thing, so we're going to have a little more time to go through the entire syllabus and give you a more in-depth coverage of the syllabus to gear you up. It's going to be on the 19th. I would have sent the link with the information, so you guys can definitely register, and so you can be a part of the marathon. All right, let me. I'm uploading the thing to the drive so I can share the link. And in the meantime, if persons have any questions about the marathon, you can ask the questions. It's going to be online, but if there are any questions, you can ask. Yes, and
Sir.
yes.
This one I go online separately from the day one we go after.
Yes, there's going to be an online one separate, right, from the day one that you
Sir,
will
so if
be
me already sign up for day one, me have to sign up for the online one again.
No, you wouldn't have to, because as I said, you will be able to join
Okay,
online
sir.
as well. Yes. All right, so let me copy this link. All right, so that's the document that we went through this evening. Well, it's uploading. Yes, so so for persons who want to register for the marathon, you can just register using the link that I would have pinned at the top right there. So again, really hope that this was helpful for you guys. If there are any questions, once you have registered for the marathon, not sure, I guess
Can
persons have
you
any
send
questions,
it
let me
again?
just see.
I left thank you back, so I couldn't see it.
What, the
Yes,
link for the marathon? All right, let me send it over. Oh, somebody posted already. Good. It's gonna be on the 19th of next month. So that's a couple of days before your exam. Yes.
okay.
Right. And if you have persons who wish to be a part of the marathon that didn't get a chance to join today, you can share the marathon link with them so that they can join and be a part of it. All right, guys. Thanks for joining. Thanks for participating.
All right, thanks, sir.
And all the best
Thank you
when
very
your
much.
exam starts. Yes, man.